Good evening, my dear J Warriors. This is your Captain Shreyas on the number one J English channel. Today, we're going to start off with alternating current, a detailed marathon for around 3 to 4 hours. It's not a very big chapter, but not a very small chapter either. And we're going to start off with the current parameters of alternating current, like average, RMS, frequency, and all of it. Then we'll slowly move on to phasors and then resistance, inductance, and capacitance in a AC circuit with LCR series. Then we'll go to resonance, then power in a AC circuit, and finally to transformers. We're going to see the detailed theory from scratch, like I did it for light waves or even electromagnetic waves. And then we'll go to the definitions, formulas, graphs, everything, apply those concepts. We'll see questions and, of course, some PYQs also. So, this is the lecture that you will need for your JEE preparation for 2026. I hope you guys are ready. Get up and quickly smash the like button, mark your attendance, and before doing that, make sure you're subscribed on to the Vedantu JEE English channel. All right. Yes. And by the way, if you check out the live section, you will see all the lectures. Even in the morning, 6 o'clock, we are taking classes. The CYQs, which is the current year questions. And of course, marathons are running for physics, chemistry, and mathematics, as you can see. And yes, after the session is over, you will see the PDF will be uploaded. This was for electromagnetic waves, something like this. The session PDF will come in the description box, as well as, we'll try to pin it up in the comments also. Okay, so I'll make sure that the comments also get pinned up. So session PDF will be over here. Click on this link and you will be able to download the entire PDF. This is for the previous lecture. Similarly, you are going to get for our current lecture as well in the description box. Okay, I hope you guys are ready. Get up, guys. Smash the like button right now. Good evening, Naveen, Suhail, Bhushan. Welcome, Rihan. Welcome, Ridhan. Namishwar, tomorrow I have chemistry exam, but still you're watching. I'm really happy. Hi, Sabrinathan, our Sigma warrior. Hi, Tanuja. Ready? Very good, Ramalakshmi. Welcome, Devji, Zains, Jaitra, Adishwar. Welcome, everyone. All right. So it's time to begin the class. I know you are pre-boards, everything are going on. Still, you are watching it. So I'll keep it very fruitful and to the point, but also detailed at the same time so that you do not miss any concept. Now, when we talk about alternating current, when we talk about alternating, second guys, okay, when we talk about alternating current, it means the direction of the current keeps on changing. So alternating means it alternates from this to that to this. I'm alternating. That means sometimes I say this, sometimes I'm saying that. So that is alternating current, where the direction, the direction, the direction, the direction of current, the direction, the direction of the current keeps keeps changing, keeps changing. So that is basically called alternating current. Now, the most common example is a sine wave, but there are other examples also of an alternating current. For example, imagine this is current versus time graph, and let's say your current goes like this. This is also alternating current, guys, because first the current is positive, then negative, positive, then negative. Positive might mean maybe the current is going clockwise. Just Chumma, I'm taking some example. And negative might mean the current is changing back to anti-clockwise. So once clockwise, once anti-clockwise, then goes like this, then goes like this. So that is an example of alternating current in a graphical way. So usually you use graphs or charts to express how the current is changing with time, because it becomes very easy via a graph to see how frequently it is changing, what's the maximum value of the current, when is the current so and so. So gaining that information becomes easier when you have a graph in front of you. Even this is the most common example of alternating current. So you can see the current is keeping on changing. Even the voltage will change, by the way, similarly. So once it is positive, then negative. Once it is positive, then again negative. Positive means it is flowing this way. Negative means it is flowing the opposite way. So that is your alternating current. So it need not be a nice sine graph. It could be a triangle, it could be a square, it could be anything which is up and down in a periodic manner. So any graph which is up and down in a periodic manner, once positive, once negative, those graphs will represent alternating current as long as the direction changes. So from positive to negative. Is this concept clear? Yeah, we'll be solving problems also, but Surya, remember this is a detailed marathon. So if you have already done the theory, if you're expecting only problems, this is not the lecture, because I have to take care of many kids who are probably not learned the theory or never understood the theory, or maybe have it as a backlog. Yeah. Okay. Now, what are the main parameters that you talk in case of a alternating current or alternating voltage? It could be voltage, it could be current. It's the same kind of graph which will be there. Instead of current, which will be measured in amperes, voltage graph will be measured in volts. That's the main difference. Now, the regular voltages that you get in your home is 220 volts and 50 hertz. You might have seen it on the adapter or a charger, or maybe some electrical appliance like a geyser or a iron box. 220 volts, 50 hertz. How many of you have seen these numbers in some or the other electronic or electrical appliance? Have you seen this? Yeah. So we'll talk about what this number is, and if, by the way, we have many kids who watch us from United States also and many other foreign countries. I check the analytics. We have around close to 5% to 10% of foreign audience also. So 90% or slightly more are Indians, but many people even from US, Australia, Bangladesh, Nepal, we have Sri Lanka, Pakistan, UAE, Africa, even from Europe. A lot of students, or maybe I don't know, even teachers might be watching. God knows. Yeah. So uh, the point is that if you are probably from the US, you will see that the number is slightly different. It would be 110 volts and it would be 60 hertz. So depending on which country you are in, this figure might change. In our country, in India, it is 220 volts, 50 hertz. In some other countries, it is 110 volts, but 60 hertz. So it depends on their history and their culture and whatever their rules and laws are and how the things have been followed. But what do these numbers exactly mean? This 50 hertz means the frequency. So if I take one time period, so from one peak to another peak, or one valley to another valley, or from one zero to the next identical zero, so that becomes t, which is nothing but your time period, the time period of that particular alternating current. And then you have the frequency, f, which is 1 divided by the time period, which is obviously going to be measured in hertz. 1 hertz is nothing but second inverse. So 1 second inverse is basically a hertz. So if I say 50 hertz means 50 times it goes up and down, 50 times in 1 second. 60 hertz means 60 times in 1 second. So usually that is the range of alternating current. Now you can also write angular frequency over here. You also have angular frequency, and the symbol for that is omega, and that is obviously 2 pi f, and the unit for that is radian per second. Just like in waves or in simple harmonic motion, you had it same way, you have that same quantity omega, which is 2 pi f, angular frequency. Remember, one complete cycle from here to here is 2 pi radians. So angular frequency tells me in radians how many times it is oscillating. Example, if I tell you that my omega is, say for example, 6 pi radians per second, it means my 2 pi radians is happening 3 times in a second. So there are 3 oscillations in a second. That means this will be my f. So the frequency will be 3 hertz basically. So 2 pi, how many times is there? That is your angular frequency, because 2 pi radians corresponds to 1 oscillation. This 2 pi radians corresponds to one oscillation, one wave, one complete circular motion, like that. Okay, that's the meaning of it. All right. Now, another parameter which you should be aware of. So I'll just put that example. So omega, if I tell you, is 6 pi radians per second. It is 2 pi multiplied by 3 hertz. This is basically one oscillation completely. Similarly, the next parameter that you should be aware of is this particular thing, which is nothing but your amplitude. So you can call it A or V naught or I naught depending on what it is. In this case, it is V naught because it is a voltage graph. If it was a current graph, it will be I naught. So V naught is basically the voltage amplitude. Any wave will have an amplitude from peak to the mean value. How much is the difference is called as the amplitude. So this is called as the voltage amplitude. You can similarly have for a current graph I naught, which is called as your current amplitude. This is current amplitude. So basically this amplitude is also the max value that the voltage or the current can get. So this is the maximum value magnitude wise which you can get, for that voltage or current. So this is the maximum value, modulus means the magnitude of it, which you can get. Okay, these are standard things which you have even learned in the waves chapter or even maybe in light waves chapter. Okay, sums will become after every concept. We'll start off with the sums, don't worry. Now you might be wondering, sir, what is this 220? You still did not tell that. Is 220 this maximum voltage? Actually, it is not. You are seeing this number as 311, but the parameter mentioned on most of the appliances is 220. So what is this 220? What is this 311? You will get an idea. But for that, let's talk about something called as the average. Average. Simple average. There are many kids in the school. What is the average height? So you measure everybody's height and you divide it by the number of students. It's just that. So when I try to find the average value of current or voltage, so the symbol for that is nothing but triangular brackets. It's nothing but the sum of the currents at different time upon the number of samples that you have taken, upon the number of counts or the samples that you have taken. Current at this point, this point, this point, this point, this point. I've taken 10 currents and I want to find the average. So I will take those values, add them up and divide it by the number 10 to get the average value. Simple. Same thing I can also talk about average voltage also. Average voltage will be nothing but the sum of all the voltages, the sum of all the voltages upon the number of samples that you have taken, upon the number of samples that you have taken. Now what happens is when you take an alternating current, like this, second, when you take an alternating current, doesn't matter what it is, whether it is voltage or current. Okay, the point is the graph goes so nicely up and down. The graph goes so nicely up and down like this. So whatever positive values are there, that many negative values are there. As many negative values, that many positive values. So the positive values equals the negative values, because of which what happens is this particular numerator that you have, the sum of currents. So if you take one complete cycle, in a complete cycle or a oscillation, in a cycle, what happens is the sum of currents, will become zero. If you have 1 ampere, you have minus 1 ampere. If you have 0.1 ampere, you have minus 0.1. If you have 0.2, you have minus 0.2. So the sum over an average cycle will become zero. That's why the average of a cycle will always be zero. The average of a sine cycle, cos cycle will always be zero. Is that making sense, everyone? Now, why is this average value important? I will tell you. Because if you use a galvanometer based voltmeter or ammeter, voltmeters can be digital, it can be made of something else also, it can be, different types, but a voltmeter which is based on, or an ammeter which is based on galvanometer. Everybody remembers it from the chapter of current, electricity, magnetism. You have a coil, current passes through it. Because that current passes, there is a magnet. It deflects depending on the current, and the needle moves, and you measure how much current or voltage is there. Yeah. So the current decides how much the deflection is, and more current will have more deflection. If you change the direction of the current, the deflection will go on to the other side of zero, towards the negative side. So now what happens is, this nobody will tell you guys, but this JEE has asked questions, and many kids get confused because they have not heard only about this concept. The reason why you learn about average is because if you use a galvanometer to measure the current or voltage, you will get always the average value. So this average value is what you get. This particular average value is exactly the reading by a voltmeter or an ammeter based on a galvanometer. If you use a galvanometer based ammeter or a voltmeter, you are always going to get zero value, because once the current will go one way, so the galvanometer will move like this, but then the current will move other way, the galvanometer needle will move like this. So it will go positive, negative, positive, negative. But do you think it will go so slowly? Do you think it will go so slowly? No. It will go at 50 hertz. 50 hertz means 50 times in 1 second. It will not be able to, before it decides to go here, the current has changed. It will be like, bro, listen, I will not move only, I will show you average value. So it will, before vibrates, it will be like minute vibration, and it will show zero. That's all. So that is the reading shown by a DC voltmeter or a DC ammeter. This is called as a DC voltmeter or DC ammeter, because you can't measure AC with such a voltmeter or ammeter based on galvanometer. So that is the purpose of you learning DC voltages, or sorry, average voltages or average current. But obviously, you will be now tempted, sir, if I want to actually measure current or voltage, then what do I do? So in such cases, you use a completely different new kind of device to measure how much AC or how much AC voltage or current is there. So those are called as hot wire instruments. We'll talk about it in a bit, but for now, remember the reading by a regular voltmeter or ammeter based on galvanometer, that is basically a DC voltmeter, a DC voltmeter or a ammeter shows average value of AC. This is a very, very important line. Do not ignore it. It is looking very simple, but when problem comes, you should be able to remember this concept and directly mark the answer. Okay, whether it will be zero or whatever it is. All right. But if somebody decides, no, sir, I will not take one complete cycle, and if I take only half of the cycle, then obviously the answer is not zero. So if you take any half of that cycle, so any half cycle, if you take, unlike before, the sum of currents, if you take the sum of currents, now whether that half cycle is here or here, so it will depend. So if I take only the magnitude of it, either this or this, even this is a half cycle, by the way, even this is also a half cycle, even this is also a half cycle, then the sum of current will not be zero, and therefore the average value will also not be zero. How much it is, I will come to it, but definitely for any half of that cycle, it will not be zero if you are taking only positive half or only the negative half. Is that clear? Why do we calculate average value only after half cycle? If full cycle average is 0, then why half cycle? So we might be interested in knowing, because the total average is always 0. Okay, we know that. So no point talking about total average for a complete cycle. We are interested in how much is the magnitude on the either side. Just like amplitude. Amplitude tells me the extent of maximum displacement. So the average value will tell me how much on an average it is going on this side or that side, just to gauge how much is the extent of the spread of that AC current or the voltage on this side or this side. That's why we need half cycle. Okay. All right. Yes, Rajshekar, definitely, man. Definitely. I hope this is absolutely clear. Okay. So what is the mathematical definition? You have learned this in AOI, application of integration, area under the curve. How many of you remember this? Average value definition, mathematical definition. Any function that you take, the average value is defined as integration y dx divided by the the duration for which you are taking the average. So the average current is nothing but the integration of the current, that means the area under the curve, divided by the duration, that means T2 minus T1. That's it. That is average. Do you remember this? Yes, Savri, Lewis? Yeah. Yes, Naveen, but we won't be doing too many of those kind of questions because I am doing from the scratch till J means level for now. J advanced will tackle it after January, because if I do it right away, then it defeats the whole purpose. Then it will take more time for me. Okay. Right. Perfect. Great. So this is the definition of average, mathematical definition. So if you want to write it in a much better way, this is how I will write it. The average current or even the voltage has the same thing. It is nothing but area under current versus time graph, whole thing divided by the time duration for which you are measuring it. The time duration for which you are measuring it. The time duration for which T2 minus T1 is the time duration for which you are measuring it. So this is a easier way to look at it rather than that integral way. You can always understand area means integration, time duration means the limits T1 and T2. Okay. So what is the value of average current in sine and cosine? Sine graph, cosine graph, whatever you take, the average will always be 0. So even if you sit and integrate it, you will see that the average value, even via integration, ends up as 0. So this is a known fact. The total area under a sine graph, or even if it was a cosine graph, I know the area will be 0. So always the average for a sine graph or a cosine graph will be 0. But that was not the only purpose. We already knew that as a fact. So what will be the answer if it was a half of a cycle? So if you take half of a cycle, the only thing that will change is the limits of integration. Instead of going from 0 to t, you will be going from 0 to t by 2. So you can see I'm taking the limits from 0 to t by 2, and the denominator also will have just t by 2. Denominator will also have t by 2, that 2 has gone on the top, but yes, it will be t by 2. So in such a case, if you perform that integral, it so happens it comes out as 2 by pi. So the average of sine or cos, if you take the average of sine or even the cos value, so for a half cycle, positive half cycle, so this is a cos graph, if you take the average of it, then it comes out as 2 divided by pi. But obviously my current will have some value, maximum value. It will not be 1 or minus 1, it will be I naught. So that's why you multiply it with I naught. So if it was a simple sine graph, the sine graph will only go plus 1 minus 1 plus 1 minus 1, right? That is the maximum value, plus 1 minus 1. So if it is a current graph, it will go plus I naught minus I naught plus I naught minus I naught. So that's why you just multiply with I naught to just specify the average current. Otherwise, average value of sine or cos is just simply 2 by pi. If you change that plus 1 to plus I naught and minus I naught, so obviously it will be 2 I naught by pi. as the average value for half the cycle. Okay, this integration you can do it very easily. I mean, just have to use the limits 0 to t by 2. That's all. Yeah. Okay, so that is the average value of the current for a half cycle, and average value for a total cycle is always going to be 0. So remember these numbers. Total cycle, it is 0. For half the cycle, it is 2 by pi times the amplitude. 2 by pi times the amplitude. The amplitude is I naught. If it is voltage, it will be V naught. Okay, for current, it will be I naught. For voltage, it will be V naught. Yes, perfect. Now let's talk about the next concept. If you are clear till this point, let me know if everything is okay. Give me a thumbs up, guys. Perfecto, capto. Okay. Everyone. Yes. Hi, Arju. Yeah, the average value of a sinusoidal of half cycle while over a complete cycle. Yes. Correct. Is RMS. What is this RMS? Root mean square. Root mean square. Now, when you think of RMS, right, always go exactly the reverse to understand it, or formula if you want to write it down. Square, then the mean, then the root. If you look at it like that, the formula will look very easy. Squaring. So I have many numbers. It could be heights, it could be marks, it could be currents, it could be, I don't know, money, it could be any numbers. So you take those value. So you take value 1, then you take value 2, etc. and you square it. Value 1 square, then you take the second value square, then you take value number 3 square, like that. That is square done. Now mean means average. So if you want to take the average, you add all of these numbers till whatever it is. So the nth value, the nth value square. Average means you have to divide it by n. Root, that is the last thing you have to do. So put this under the root. What you get over here is the RMS value of that sample. So if I have a sample of n numbers, then the RMS value is taking the squares of each value and then their mean and then placing it under the root. That is RMS. Is that clear? So always look at it in the reverse order. The formula looks very easy. But if you think of root of mean of square, then it might be little bit confusing. Now, average current is not equal to RMS current. You might be wondering, sir, why on earth do you need RMS? I have asked this question to so many people, even sometimes teachers, while taking interviews, and believe me, not many of them know it. Formula, yes sir, I know. V1 square plus V2 square plus V3 square divided by n, whole thing under the root. Why RMS? Why not cube? Why not raised to 4? So that is what many people get confused or don't know why that comes. So I'll just give you an overall picture of why it comes. Basically, RMS current means, say for example, you have AC current. You have like this AC current. This is your AC. This AC current is example passing through a resistor. This current, AC current, is basically passing through a resistor. This will generate some amount of heat. Now it doesn't matter whether the current is going left side or right side. Both times the heat generated, the rate at which energy will be generated, power loss will be nothing but I squared into R. So this is the energy generated per unit time. So you can find out the total energy generated by integrating it. So the total energy generated, so that will be IAC square into R into dt integrated for that entire cycle. That means 0 to t. This is the total energy generated over a complete cycle. Are you understanding it? Remember, power loss is I squared into R. So this is d, power loss is rate of flow of energy. So if I take dt on the other side and I integrate it, I will get the total value of the energy which will be generated in that resistance over a cycle. Now, imagine, this is so crazy to figure out how much energy it is consuming, because AC, when it flows through a device, heater, fan, whatever, it will consume energy. To find it out via integration, I really don't like it. I'm not a fan of integration, because every time physics teacher will never be a fan of integration. Yeah, integration, we know, we do it, we love it also sometimes, but we'll try to think what is it that I can replace that integration with. Like we had moment of inertia. Moment of inertia, yes, it is an integral formula, but I don't want to perform that integration every single time. So we defined quantity, so which comes out as a standard value for all the rigid bodies, and we use it, as a direct result. So, my dear students, imagine now you have a direct current. You have basically a direct current. This is a DC current. It will be constant value. And that DC current is passing through that same resistor. That DC current is passing through the same resistor, but it ends up generating some heat. The energy which is generated is I squared DC into R. This is power multiplied by the time. Imagine these two happen to be equal. The energy generated by this DC and the energy generated by this AC just happen to be equal in amount. And in the same time, in same time period of the cycle. So when one cycle is completed, you pass the DC current for that same duration and you find out same amount of heat is generated. That DC current which is flowing is now like a replacement, is like an equivalent current, which is constant current, which can produce the same energy, same heat in that same time. So instead of taking some crazy integration, crazy areas, varying currents, I will say, listen, boss, you don't worry about those varying currents. Just take this DC current, which has the same energy loss in that same time. That becomes simple. Instead of saying the current is now 0.1, then it is 2, then it is 5, then it is 2, then it is 1, then it is 0 and minus 1. Arey boss, what is the heat generated? Very difficult. I'll tell you, listen, you take the current as 3 amperes, whatever energy loss will happen using 3 amperes, that is the answer. You will be so happy, because now your problem is simple, because DC is always easier than AC. So that current, that DC current, that DC current, that constant DC current is basically called the RMS. Is called basically the RMS. Is that clear, everyone? All right. How many of you got it till now? Let me know quickly in the chat box. And that is the reason why when you equate both of them, it's not a big thing. If you equate both of them, you will see R will get cancelled. The time will come before, and that's why you see squares and all of that. That is why RMS formula has squares and not anything else. Yeah? You don't have to remember this formula. This is nothing but power, no? What was this? This is nothing but power. Power is nothing but I squared R. So into time will give me, and joules per second into the seconds will give me the joules of energy being consumed. So I don't have to remember it. I know it by deduction, logical deduction. Power into time will give me energy. So from this only you get the formula for RMS. Okay, from this only you will get the formula for RMS, because if you equate them, you are going to see integral IAC squared into R into dt from 0 to t will be basically equal to integral of I squared, that DC is only called as RMS now, into R into t. but I don't have to integrate. Sorry. So that will be nothing but integral I squared RMS into R into T. So you can clearly notice this R and this R has got cancelled, and therefore you are going to get IRMS is going to be equal to IAC squared dt integration from 0 to t whole thing divided by the time period, but that will be the square. So if you take the root on both sides, IRMS will be root of this entire thing. So that's why I said you have to take the sum of the squares divided by the sample size and then put it under the root. That gives you exactly the RMS value. So this is okay if I have finite values, but if I have infinite values, then you do integral of that value with respect to time from 0 to the time period upon basically the time period value square, sorry, and put it inside the root. That is also going to give me RMS value. RMS value. So the square of the value is integral in that time period upon the total sample size under the root will give me RMS value if it is a function, continuous function. If it is discrete values, then you are going to use this formula. How many of you got it now? Finally, what is RMS and where does it come from and what does it really mean? Got it? Clear? Perfecto? Amazing. Now, that is also given over here. So the what is the formula? I've just given it to you. It is nothing but integral I squared dt from one time period upon the total sample size, which is the total time period of that particular function. And if you do that operation for a sine wave or for a cosine wave, doesn't matter, then the average value of the square of the sines, comes out as half. So when you put it inside the root, when you put this inside the root, you are going to get 1 by root 2. You are going to get 1 by root 2. So for a sine square, the average is half. The root of that will be 1 by root 2. So if I have a normal current or a voltage graph which goes up till I naught, comes till minus I naught like this instead of plus 1 and minus 1, the RMS value will be 1 by root 2 times of that I naught, or if it is a voltage graph, it will be 1 by root 2 times of the maximum voltage. That's the only difference. That's the only difference. Okay. Why do we square the current in the RMS? I just explained it to you. That was the whole purpose of this derivation, my dear. If a AC current is passed, this is the energy which is lost. If you pass some amount of constant DC current for the same loss in the same time, then this is the formula. Because the energy loss is same, so I equate this with this. R gets cancelled, time comes below. So IRMS is this. So you can see square is there over here. It is basically integration means sum of it. So if I take the sum of the squares and divide it by the sample size and put it inside the root, I get RMS. That was the whole purpose of this derivation. Okay. So it does not depend on the sign, because when you square it, anyways the negative square will become positive. So the sign will not matter whether it is negative cycle or positive cycle. Yeah, because the moment you square it, it's gone. So RMS value is I naught by root 2 or V naught by root 2 for a sine or a cosine graph. Now you should also know roughly what is the value of 1 by root 2. Sometimes you might need it. 1 by root 2 is roughly 0.707. Okay, since the value of root 2 is approximately 1.414. So it is 70% of the maximum value. So on that sine graph, if somebody decides to draw what is the RMS value, this will be approximately 70%. This will be 70% or basically 0.7 times of I naught. So this constant current, if it is passed, it will generate same energy as that AC current. So almost 70% of that current generates, or the maximum value, generates the same heat as the AC current with varying values. Okay? Yes. So RMS will be greater, correct? Because RMS will ignore the signs once you square it. So now coming to the point where we spoke about uh, this particular appliance, that 220 volts, my dear, is always RMS. So any device, they never mention maximum value. They always mention RMS. Keep that in mind. So if RMS is 220, what will be the maximum value? Maximum value by root 2 was RMS. So if you multiply RMS with root 2, that is 220 into root 2, you are going to get 311 volts approximately. So that is the maximum value till which the current goes up. 311 plus, 311 minus, 311 plus, 311 minus. But the constant current for that heat will be 220. Is that now clear? Any electrical appliance, any AC problem, by default, they will mention RMS. And let that sink in inside your head. Any AC problem, unless specified otherwise, will always tell you RMS, guys. Always tell you RMS. Now, that is what is the case for almost all the things. So in India system, the voltage supplies 220 volts, 50 hertz. So the frequency is 50 hertz, 220 volts is the RMS. So the current will become zero two times in every cycle, once in the positive cycle and then in the negative cycle. But other times it is either positive or it is negative. Okay. So this is very interesting, guys. So 220 volts is always the RMS value. Now, if you remember some time back, I had told you that if you use a regular voltmeter or ammeter, which is used for measuring DC, for AC, it will give zero values, basically the average values, which is of no use to me. That's why you use special instruments, which are called hot wire instruments, and they give you RMS values. So this is also a very crucial piece of information which I should mention over here. So hot wire instruments, hot wire instruments, they give you the RMS of that particular AC, and this is the instrument that you will generally use for measuring most of the currents or voltages. You don't have the working principle, but this is the device used to measure currents or voltages for most of your electrical appliances around your house. Okay, so keep this in mind. Hot wire instruments measure the AC current or AC voltage. So if you know the RMS, from RMS you can figure out what is the maximum value also. So from RMS you can also figure out what's the maximum value. Are these concepts clear in your head? Yeah. Shall we do some questions now coming up on your screen? And here it is. First question comes up on your screen now. The frequency of an alternating current is 50 hertz. What is the minimum time taken by current to reach the peak value from the RMS value? Interesting. Frequency is given. So from peak to reach its peak value from RMS value. So keep in mind, one thing I had to mention you before going ahead, uh, right at the beginning. So whenever you have AC voltages and currents, the function, of current or voltage, how does it look like? This was very important. I had to give this off. Okay. So if you have current, usually it is given like this: I naught sine omega t. If you have voltage, usually it is given like V naught sine or cos omega t. You can also use cos anything. It's completely up to you. So you can also write it as I naught cos omega t. Also, this is V naught cos omega t and all of that. Omega is your angular frequency and V naught or I naught is basically your amplitude, just like a simple SHM. Okay, so this is how the current or voltage as a function of time is specified in alternating current. Okay, this is something which you should be aware of, just like in simple harmonic motion. So now it's good time that we solve this question. So for an AC circuit, how much time does it take to reach peak value from RMS value? So let's take, for example, the current as I naught sine omega. Omega is 2 pi into F, which is basically 50 into T. So as good as saying I naught sine 100 times pi multiplied by T. Instead of F, I have put 50. Keep in mind that this 2 pi F is only omega. This particular 2 pi F is exactly omega. Okay. Now let's take the two time instants. First, when it is at its RMS value. RMS means what? RMS means what? It should be having I naught by root 2 value. So that will be equal to I naught sine 100 pi into T. This is the time instant when it has just reached the RMS value. I naught will cancel. So basically sine of 100 pi T1 will be 1 by root. Whose sine is 1 by root 2? It is pi by 4. So therefore 100 pi T1 will be nothing but pi by 4 sine 45 degrees. Pi will cancel. So T1 will become 1 divided by 400. 1 divided by 400 seconds when it has reached RMS. Similarly, let me figure out when does it reach the peak value. So if it has reached the peak value, the value of the current will be I naught only. So this will be equal to I naught sine 100 pi some other time. So therefore, sine of 100 pi T2, I naught will cancel, it will become 1. Whose sine is 1? The angle which is basically 90 degrees. So this internal angle will be pi by 2. So pi will cancel and T2 will become 1 divided by 200 seconds. But the question is, what is the time duration that it takes? So our final answer delta T will be nothing but T2 minus T1, this time minus this time. So 1 by 200 minus 1 by 400. So this will become 1 by 400 of a second. So 1 by 400th of a second, guys, what is this going to be? This is 1 by 4 or this you can say 1 by 4 into 10 to the power minus 2. 1 by 4 is nothing but 0.25 into 10 to the power minus 2, which is nothing but 2.5 into 10 to the power minus 3 seconds. So 2.5 into 10 to the power minus 3 seconds is the B option. Okay, so this is how we have just used our basic equation of current or the voltage to figure it out. Yes, option B. Very nice. So most of the time, simple mathematics of trigonometry or SHM will help you. So if you have not yet learned SHM, so it's a good time to go back to SHM and do it. But if you want me to do it, it will take some time. All right. I've not yet planned it, but maybe in the near future, I will do SHM on the channel. I have already done it 2 years back, 1 year back, last year and all of that. So you can check out those old classes. But if you're looking for a fresh one, it is going to take a little bit of time because right now we are focusing more on 12th syllabus. Okay. An alternating current is represented by this equation. What's the RMS current and the frequency? What's the RMS and the frequency? Sir, if they didn't mention, should we always take AC voltage in the question as RMS? Yes. Unless specified otherwise, always choose RMS. Okay. Not average or peak or anything else. Okay. Unless specified otherwise. Very good. Very good. Very good. Great. So let's do this question, guys. What do we have? 100 pi t. This 100 pi is basically omega, and omega is exactly 2 pi f. So 100 pi is 2 pi f. So f will be pi goes, it will become 100 divided by 2, which is nothing but 50 hertz. So 50 hertz is only there here and here. Other two options naturally will get eliminated. Now, out of the two, how do I choose? This value outside is always the amplitude. So if I want to find RMS current, it will be nothing but maximum current by root 2. So it will be nothing but 100 root 2 divided by root 2. Root 2 cancels and I will get 100 amperes. So 100 amperes is there over here. So D option is the correct one. Yeah, very good. D option, D for IIT Delhi. Very good, Sabrinathan, Abhinav, Harsh, Louis. Very nice. Keep it up, guys. Keep it up. Proud of all of you. Now let's go to the next question. Now you're getting a hang of it. And now comes a bouncer question. Look at this. This is what will happen, right? And this type of questions have come in JEE mains. Current is I1 sin omega t and I2 cos omega t. What is the RMS current given? Now I'll tell you, there are two ways of doing this question. There are two ways of doing this question. First method is where you go purely by definition, and by definition RMS current will be integral I squared dt by the time interval 0 to t. So when you do this method, what happens is you'll have integration, you will have this whole thing I1 sine omega t plus I2 cos omega t whole square dt 0 to t and whole thing by t. Now just imagine the length of this problem. So you'll have basically I1 square sine square omega t and then dt, first integral 0 to t. Then you will have second integral I2 square cos square omega t dt as the second integral. Then you will have 2 times I1 I2 cos and sine everything. So sine omega t cos omega t, and there is dt, and then integral 0 to t, and then whole thing divided by t. I mean, you get tired even writing it. Just imagine doing this in the exam. But I'll just show you methodically if you do it. Okay, using standard definition. Oh, by the way, this is IRMS square. So sorry, I also have to put the root. So if I just go pure methodically, this is how long the problem will become, because I have to open up the brackets. A plus b whole square is a square plus b square plus 2ab. Then you will think, okay, this is I1 square, and this over here, if you notice, sine square omega t dt divided by t, okay, from 0 to t. First term, second term, I2 square integration of cos square omega t dt whole thing divided by t 0 to t, and then over here I1 is there, I2 is there, divided by time period, and 2 sine cos is sine 2 theta, so integration of sine 2 omega t dt again from 0 to t. Now if you do this in this particular manner, again, so long, guys, you have to now think, what is this, and what is this? Actually speaking, this particular quantity over here is nothing but the average of sine square. If you notice this particular quantity over here, this is average of any cos square quantity, and this particular thing is nothing but the average of sine to omega t. Doesn't matter whether it is 2 omega or 3 omega, it is just the average of any sine quantity. Now what happens, what is the average of sine square? I had given it to you just some time back. If you remember these values, it is very easy to solve the question. Where was it? The average of sine square or cos square is half. The average of sine square or cos square is basically half. So this is basically half. So therefore, this will become I1 square by 2. This will become I2 square by 2. Average of a sine is always 0. So this will just become I1, I2 multiplied by 0. So this is your IRMS square. So therefore, my IRMS will be root of I1 square plus I2 square whole thing divided by 2. This quantity has become 0. Do you see the length of the question? It is very long. This is the answer, but this is very, very long because it is pure mathematical. There is no physics in it. Yeah. But any ninja technique, any capto technique, I'll tell you, very simple, man. Now I will teach you like a physics teacher, not like a maths teacher, because I'm pretty sure maths teachers will love this method because very nice integration is there. Concept of area under the curve is there. Concept of average of sine square and sine is there. So all these concepts are there, very good maths, no doubt about it. But you know how I will think? I'll think like this. I will think there are two currents passing through a resistor. Just imagine if this particular I1 sine omega t were to pass through some resistance, how much current, constant current will I need to produce that heat? To produce that heat, how much constant current will I need to produce the same amount of heat in that particular resistance? I will need I1 by root 2 constant current for same heat, for the same heat to be generated. Similarly, if I2 cos omega t current went through this particular resistance, some heat will be generated. Doesn't matter whether it is sine or cos. I will need I2 by root 2 constant current for same heat. Now if both of them if both of them are going together, in that circuit, in that same resistance, if both currents are going, how much will be that constant current which will generate the same heat? That's the idea. So here is the answer. The total heat generated will be heat due to 1 and heat due to 2. What is the heat which is generated due to this current? It will be I squared into R. What is the heat generated due to the second current? It will be I2 by root 2 square into R. Heat generated due to this current, will be the total heat generated due to these both currents will have IRMS value as a constant current which will generate same heat. So I will put IRMS square multiplied by R over here. Just check if you understood this equation. So when both the currents move in the same resistor, that constant current which will generate the same heat is called RMS current. So how much heat will this current generate? I squared into R. So this total heat will be if this current was passing and this current was passing and producing independent heats. R cancels, and what are you getting? I1 square by 2 plus I2 square by 2 is nothing but IRMS square. So naturally you are getting IRMS is root of I1 square plus I2 square divided by 2. Now you only tell me, is this method better than this particular method? It looks like garbage right now, but this is so powerful and easy. I have explained you, that's why I've written down so many things. But actually, many kids directly start with this equation. They don't even write all these things. They think, oh, the total heat which will be generated will be whatever is the RMS current totally squared into R. That's how your opening statement will be. And this current will generate some heat. This current will generate some heat. If I add their heats, that will be the total current's heat. So R cancels. And you just do the simple math. You will not be even doing this. This was just for explanation. Yeah. Oh, you went with this method? Then I'm really super duper proud. Okay. So this is how you can solve it, my dear students. Now, a similar question came in 2025. But instead of a sine and a cos term, one was a constant term and the second term was a sine or a cos term. Now it doesn't matter whether it is a sine or a cos, even this phase does not matter, plus pi by 6, minus pi by 6, plus pi by 2, it really doesn't matter. This is chumma there to confuse you from the main problem. So what do you do in this case? Same concept let's apply. Let's not go by pure mathematics, guys. Let's use our same concept. So now we have already a resistance and in which already 5 root 2 amperes of constant current is going. Already it is going. This is no longer AC. This is just a DC current. Keep that in mind. So the heat which it will generate, the first thing will generate will be I square, which is 5 root 2 square, 5 root 2 square multiplied by R. This is the heat generated by only this much part. Now pass the second current. How much is that second current? Guys, yeah, this is that current. 10 cos blah blah blah, amperes current is passing. The RMS value, the RMS value, the RMS value of this will be 10 by root 2 amperes of constant current, because 10 is the amplitude. So 10 by root 2 amperes is the RMS value. So how much will be the heat generated by this? It will be I squared, which is 10 by root 2 square into R. That's the heat which will be generated because of this much AC current. So I have taken the equivalent constant current, which is RMS. So I squared R is the heat generated. Now you just have to add them up. So for the entire circuit, so the total heat which will be generated will be the total RMS square into R. That will be the sum of these two heats. That means 5 root 2 square into R plus 10 by root 2 square multiplied by R. That's all. So now we can see R as usual will get cancelled, and we are going to get 5 root 2 square, 2 into 25, that's 50, plus 10 square is 100, 100 by 2 is again 50. So this is going to be 100, but that's RMS square. So my RMS will be square root of 100, which is 10 amperes, which is obviously option A. Option A. If you go by the regular method, it is going to be very, very lengthy. Do not do that. In the exam, just calculate heat by the first component, heat by the second current, and then add their heats. That will be the total heat. Total heat will be the total RMS square into R. That's it. Very good, Louis. That's the spirit. Loved this method. How many of you found this method very useful and very interesting and very revealing? Yeah, like a truth being revealed, physics wise. And you see how physics can overpower sometimes, rather than your regular solutions. And if you have loved this, please make sure you are liking this video. Do not forget to even subscribe to the channel. Many times you forget. Okay, cool. Amazing. Amazing, guys. Now let's do the next concept, and that is basically our phasors. So just a quick revision of what phasor was. See, this graph looks all good for current or voltage. Current is 0, maximum 0, minimum 0. How much is the time period? What is the amplitude? What is the frequency, angular frequency? Everything you can get. But often, whenever you have such periodic quantities, the better way to deal with them is taking a imaginary vector which rotates with the same angular speed as this wave's angular frequency, and that vector which rotates, it's an imaginary vector, that is called as a phasor. And the phasor is such that if you take the projection or a component of it, it always gives me the value of that wave. For example, right now my phasor is horizontal. If you take the y component, it is 0. So if you see in this graph, the y value is, or sorry, the actual value of this graph is also 0. So after some time, this phasor will rotate. Let's say the y component is this much. That's exactly the value at, some time. After some more time, it has gone here. This is the y component. This is the value in this graph. After some more time, it reaches here. This is the max value which you can go up by. So that also is the amplitude. After this, you can see my y component will reduce. And when it reaches here, again the y component will become 0. When I go down over here, you can see this is my y component. This, when it goes, rotates by 270 degrees. This is my least value which I can go. On the other side, the least value or the maximum negativeness I can get. Again, when I go over here, the y component reduces. Again, go here, y component reduces. Again, I reach here, 360 degrees completed, I will get 0 value. So this is basically, this rotating thing is a phasor, and this phasors component gives me the numerical value on this time graph. Second thing, the length of the phasor, if you measure the length, is always going to be the amplitude. Yeah, the length of this vector which is rotating, or the length of the phasor, is always going to be the amplitude. The time period of revolution is also the time period of this wave, which means the angular frequency of this wave is the angular speed. Remember circular motion, omega, symbol wise and unit wise it is the same, but it is called differently. In circular motion it is called angular speed. In waves it is called angular frequency. So that is the reason why the symbol is same, and you can see units are also same, but because it is used in different context, the names are different. So here it is called angular speed, here it is called angular frequency. So they will have same angular frequency. Do you now understand what is the meaning of a phasor? So this is usually called as a time graph or a time domain graph. This is called as a phasor graph or a phasor diagram. Okay, is called as a phasor diagram. This is called as a regular time graph. So whenever I have a varying quantity, I can always draw a phasor of it, and that phasor I can treat it as a vector for my calculation purposes. Remember, vector addition we know, vector subtraction we know, how to manipulate vectors we know. So we can use my vector algebra to solve complex or even normal problems. That's the advantage of using a phasor diagram. That's the advantage of using a phasor diagram. Okay, is this clear? This is basically a quick revision of SHM, superposition and waves from 11th class. What was phasor? Yeah, everyone till this point, give me a thumbs up in the chat box. So phasor diagram is an imaginary diagram which corresponds to your regular time graph, whose amplitude is the length of the vector. The vector which rotates is called as the phasor, and the angular frequency here is the angular speed of rotation of that phasor. The component of that phasor in the y direction will give me the actual value of this time graph. Okay, now it so happens, funnily enough, that when you have your elements in the circuit, in AC circuit, whether it is a resistor, whether it is a capacitor, or whether it is an inductor, you place it in a AC circuit. This is the symbol of AC. Remember, if you had a battery, you use this symbol, it will be constant current. But whenever you put this symbol, it means the current is alternating. Once the current is going like this, then the current is going like this. Again, it is going like this. Again, it is going like this. So it is alternating current. Then it so happens that how your voltage changes and how your current changes are not in sync. Rather, there is a small difference in their phase. Something like this. Over here, I would say, if this is my time domain graph, current is already ahead, voltage is somewhere here. So if the voltage goes up like this and comes over here like this. This is my voltage. It goes till this height and comes down till this height. So this is my voltage. You will see that the current will be somewhat already ahead of it. So it is here, should be here. Okay. Something like this. It's not very exact, but you get it. Basically, you can see the current and voltage are not in sync. They both don't reach maximum, minimum, zero at the same time. So they are slightly off. And when they are slightly off, their situations are different. And situation in physics is called by the word phase. I'm in a very bad phase of life. I'm very, very nervous. So my situation in life is not great. I'm in a very happy situation. I'm in a very happy phase. So their situations are not same. That means their phases are not same. So you will see if you draw the phasor of voltage at any given point, you will see the phasor of voltage. If it is here, then the component of the current will be somewhere here like that. So you can see the current is at a different angle as compared to the voltage phasor, or their vectors have a phase difference. That phi is basically called as your phase difference. This particular phi that you see over here, this is called as your phase difference. Phase difference. Notice how voltage was a beautiful sine graph. It started from 0, went up, came down nicely like a regular sine graph. But the current is something sine omega t plus phi. So because of it, there is a small offset in that sine graph. And you can see they are not reaching their max, minimum zeros at the same time. So that is your phase difference. This occurs whenever you have a combination of these or just one of them. You will see the voltages and currents might not be always in sync. They might be slightly off here or there. Okay, so that is the reason why we are studying phasors. Till this point clear? Yeah. So the current and the voltages might not be in sync. Now usually the phasors will rotate anti-clockwise. If they are rotating anti-clockwise, which vector or phasor is ahead of which other phasor? It's like two vectors, they are rotating like this. It's obvious this current is already ahead of the voltage. So I can say current leads the voltage, or voltage lags behind the current. If this current was here and they rotate, then I would say the current is behind the voltage, or the voltage is ahead of the current. So that's how the terms are used, depending on how they are placed. And remember, always they go anti-clockwise, not clockwise, which is your customary rule even in trigonometry, where you take anti-clockwise as positive and clockwise as negative. So same rules are applicable here also. So whichever quantity is ahead in the anti-clockwise sense will be considered as leading, and the other one will be considered as lagging. So here I can say the current is leading. The current is basically the leading quantity, and in this case the voltage is lagging. But it can be the other way around also, depending on what kind of circuit it is. So in this example, this is the scenario, but if I chose the current here, then it will be exactly opposite. Okay, previous doubt also clear? Yeah. Yeah, we can draw it clockwise also, but again, it will be confusing because then you have to take a different reference. Usually, our trigonometrical references go with the horizontal line towards the right side. So that is why we are following this convention. It's not like you can only take anti-clockwise, you can go clockwise, then you have to take something else. I don't want to go into that. Okay, it will be unnecessarily complicated. Okay, sir, Okay, sir, I understood why we need phasors. What is a phasor? I understood what is the meaning of phase difference. You are telling me that these things, resistors and inductors and capacitors, cause that difference. Can you show me how? Well, why not? Let's start with a resistor first and see what exactly happens when you have only a resistor in the AC circuit. So this is a AC circuit. First I'll have only resistor, then I'll have a capacitor, and then I'll have a inductor only. And I will see in all the three cases what difference does it make. Alright, ready for it? First, let's take only a pure resistor. Okay, this is some voltage and maybe the current which is flowing in that particular circuit, just like before over here. Okay, so let's say there is some current. Oops, okay, there is some current which is basically I naught sine omega t, I naught sine omega t. I don't need this as of now. There is some current which is flowing in the circuit. I want to figure out what is the voltage going to be. So if I apply from this point, if I apply from this point, Kirchhoff's law, the voltage is at an instant V, starting from this point, and I go like this, and I come back to this point. So let me apply Kirchhoff's voltage law like this. Okay, I start from that point and I come back at that point. What I will get is the first point will obviously, I'm going from one side to the other side. So there is a potential difference of V. There is a wire, so no drop. I am going through the resistor. And when I'm going through the resistor, I'm going in the direction of the current. So definitely there will be a drop. And that drop will be nothing but minus I into R. And I'm coming back to the same point. So it will be basically 0. So therefore, voltage will be current multiplied by resistance. But I already know what my current is. This particular current, I already know what it is. It is nothing but I naught sine omega t. I naught sine omega t. This was our resistance over here. So I will take both these terms together to see what happens. So V will be nothing but I will take I naught over here multiplied by this particular R, and let me keep this sine omega t separately. Why did I do it? This is the oscillating term. This is a fixed term. So why not write this fixed term as the amplitude, and this is just my oscillating term. That means my maximum voltage is simply the maximum current multiplied by the resistance. And funny part, if the current is a sine function, even the voltage is a sine function. That means there is no phase difference. And this is the proof for it. This is the simple proof for it. Is that clear? There is no phase difference because both of them are sines. So if somebody decides to draw a graph, if somebody decides to draw a graph for both of them, this is your time, this is your time, and let's say, okay, we had our current. So let's say this is the current. Okay, this is one time period. All right. This is your current. Your voltage will be I naught into R. So multiplied by R times. So might be lengthier if R is more than 1. If it is less than 1, it will be shorter also. So anything can happen. So this is your voltage graph. The max value is V naught, max value is I naught. So this is the time graph. If you look at the phasor diagram, right, and see how it comes out. If you see how the phasor diagram is going to look like, it's going to be made up of two circles. One circle for the current, and another circle for the voltage. The radius will be their amplitudes. the radius will be their amplitudes, and at any given instant, the voltage phasor and the current phasor, will be in sync, rotating together. They will be in sync and they will be rotating together. This would be my time period, which is 2 pi divided by omega. Yeah, they will be rotating together. So this is my voltage phasor, and of course this is my current phasor. So can I say that the current and the voltage are in phase? That is no phase difference. That is no phase difference. No phase difference. Is that clear, everyone? Only for resistance, voltage and current are in sync. Okay, they are in sync and there is absolutely no phase difference. Yes, amplitudes are different, but their peaks, valleys, zeros are reaching at the same time. Yeah, perfect. Now, so resistance is frequency independent, right? No, resistance is not dependent on frequency. I'm talking about normal resistors resistance. Okay, your regular carbon resistance or a conductor's resistance only depends on temperature, area, length, and the dimension or the shape of that conductor, nothing else. Okay, and the material, of course. So that is also there over here in the same way, and we have shown the diagram, phasor diagram, and the time graph. Beautiful. Now let's probably do a question for this. Say, for example, it is given to you that the current in a AC, is given as the AC current is 20 amperes and 100 hertz. Find the voltage as a function of time if current was 0 at t is equal to 0. Find voltage as a function of time if current was 0 at t is equal to 0 in a pure resistive whose resistance is basically 5 ohms circuit. In a pure resistive circuit, the resistance of that circuit is just given to be 5 ohms. So what it means is that you just have a simple resistance of 5 ohms, you have a AC source, and that AC source is giving me some current of 20 amperes and 100 hertz. How much is the voltage? That is what we have to figure out, what is the function going to be like. First of all, let's understand over here, this 20 amps is not maximum. It is the RMS. I told you, whenever nothing is mentioned, always take it as RMS. So actually, the RMS current is 20 amperes. RMS is maximum by root 2. So that is 20 amperes. So therefore, the maximum will be 20 root 2 amperes. If this is the maximum current, you can also find the maximum voltage. The maximum voltage is maximum current multiplied by the resistance. Maximum current is 20 root 2. Resistance is 5. 25 is 100. So 100 root 2, volts. 100 root 2 volts is the maximum voltage. This particular information tells me that my voltage is sine graph. Pure sine graph, because sine will always start with 0. So at time 0, current is 0, means it is a pure sine function. So therefore, my voltage will be V0, which is nothing but 100 root 2 into sine of omega t. Wait a minute, I don't know what is omega, so we'll have to figure that out. So over here, 100 hertz is given. So omega, which is 2 pi multiplied by frequency, which is 100. So that will become 200 pi radians per second. So put 200 pi over here. So I'm just going to get 200 pi multiplied by T volts. So that is our final answer, guys. So the voltage as a function of time is exactly this. 200 root 2 sine 200 pi T volts. Perfect. Got the answer. Very good, Louis, Abhinav, Savrinathan. Amazing. Perfecto. Kudos, guys. So this is how a simple question also can come, pure resistive based thing. But obviously, many students will make mistakes here also. You might think this is simple. I'm telling you, 90% students I have seen making mistakes here because they forget it is RMS. Then instead of sine, they can take cos, or sometimes they forget something else only. Okay. Let's see what was asked in basically 2024. An alternating voltage is given applied to just a resistance. The time taken for the current to go from half of the maximum to the maximum value. Because it's a pure resistive circuit, because it is a pure resistive circuit, it is clearly mentioned. So whatever time is taken for the current, the same time will also be taken, same for voltage also. Same for voltage also, because they are anyways in the same phase, same time, everything. So if voltage is going up, current is also going up. So whatever time voltage will take, same time current will also take to go from half to maximum. I mean, its half to its maximum. This is the first thing. This is the first thing. Yes, Indumati, any doubt regarding the session or the question I'm discussing? Please ask. So what I will do is, I'll think. I want to first go from half of the maximum value. So half of the maximum value voltage will be 220 divided by 2. So 220, and then I have sine 100 pi t. 200 cancels. So sine of 100 pi t, whatever the time will be half. Whose sine is half? Yeah, think about it. Whose sine is half? 30 degrees, which is basically pi by 6. So therefore, T1 will be pi cancels, will be 1 by 600 of a second. Now go for the second part. To the peak value. Peak value means instead of voltage, I should put 220. That's the maximum value. So 220 sine 100 pi, whatever the time is. 220 will cancel. So sine of 100 pi into that particular time instant will be 1. Whose sine is 1. 90 degrees, which means pi by 2. Pi cancels. So T2 will be nothing but 1 by 200 of a second. So question is the time interval. So even before going ahead, I can multiply this with 1000. So 1000 divided by 200 millisecond, it will be millisecond. So that will be 5 milliseconds here. And if you multiply this again by 1000 divided by 600 of a second. Yeah, is that right? Perfect. So this will be nothing but 0 cancels, 10 by 6, which is 5 by 3 of a millisecond. So now the actual question is finding the time interval. So that will be T2 minus T1. So it will be 5 minus 5 by 3, which is 1 minus 1 by 3 is 2 by 3. So 2/3 of 5, which is 10 by 3 milliseconds. 10 by 3 milliseconds is 3.33, which is the B option. B for IIT Bombay. Okay, clear? How to solve this? Yes, again option IIT Bombay. So this kind of question has come in 2024 in JEE Mains. So the concept was, since it was purely resistive, voltage current will go simultaneously. So same time for both of them. So why find the current function? Just do it for the voltage function. So voltage function is given. So half value of 220 first, second time the maximum value. So we'll get two values of time. The difference of these times is the time interval. A similar question we did it even some time back. Correct? Okay. Now let's go to capacitor and finally inductor. Okay. Ready for this, guys? Capacitors and inductors. Alpha question. Wow, perfect. So what happens in a capacitor? Let's have a look. First of all, okay, so there will be some current, and because of which, that current which will go, will create some positive charge and some negative charge on that capacitance. That current will come back over here. Let us again use Kirchhoff's voltage law starting from this point, and I will come back to this point. Okay, so I'll start from that point. So I'm going to use Kirchhoff's voltage law starting from that point, and I'll come back to the same point here. So I have a voltage, AC voltage connected to a capacitor. So the first thing that I will get is V naught, or whatever is the voltage of that particular AC. There is nothing over here, minus voltage across the capacitor, and I come back to the same original point, so it is 0. So voltage of the AC, which is V naught sine omega t, will be voltage on that capacitor. Is that right? What is the voltage on that capacitor? We all know Q is CV. So V will be Q divided by C. So it will be the charge divided by the capacitance. Rearranging it further, my charge will be C times of V naught into sine omega t. This is very important. So voltage on a capacitor is charged by capacitance. Taking the capacitance in the numerator on the left hand side, you will see it is C times of V naught into sine omega t is the charge at any instant on that capacitor. Simple. Okay. Now I have an idea. I will differentiate this. Yep, I'm going to differentiate both sides. So d by dt over here, this is a constant. So I'll just do d by dt over here. Now notice what will happen instantly. dq by dt, the rate at which the charge on the capacitor changes is the rate at which the charge is entering it, meaning through the wire. So it is nothing but the flow of the current. So technically this is just I. Technically dq by dt is basically I. Okay, what happens over here? C is there as it is, V naught is there, derivative of sine omega t, omega will come outside, sine's derivative is cos, so this will become cos of omega t, of course. I will rewrite it slightly better. Okay, so I will write it like this. Therefore, I is equal to, observe this now carefully. Sorry, yes. Oh my God, why is this ringing so badly? Huh. V naught is there. V naught is there. V naught is there. Divided by, divided by, divided by, observe this. C and omega were in the numerator, right? Deliberately, I will write it in the denominator. Why I am doing it? I'll explain you, but for now, mathematically, there is nothing wrong. I just taken the numerator term as 1 by 1 by. It's the same thing. And over here, I will write, instead of cos, I will write it as sine omega t plus pi by 2. And sine in the second quadrant is positive, all silver teacups. So it is positive. So sine of omega t plus pi by 2 is still going to be cos omega t. Nothing wrong in it. Everyone fine? Okay. Now, what is this equation feeling like? What is this equation feeling like, and why I have done it in this manner? Because my final value of the current, you know how it will be? I naught maximum. This is a constant value. V naught cannot change, C cannot change, omega can't change. So that those are numbers. So it is just I naught. And then I will just have sine of omega t plus pi by 2. A lot of things to observe. First thing to observe, my voltage of AC was a sine graph, but my current is a sine graph with an extra phase of pi by 2. So are they in sync? Obviously not. There is a phase difference of pi by 2, which is 90 degrees. Who is ahead of whom? It's obvious that current is ahead because plus pi by 2 of the voltage. So they are no longer in sync. So if at all I look at the graph of them, notice how it is. This is voltage graph. This is your current graph. This is your voltage graph. And this is basically your current graph, guys. This is your current graph. See how the current is already ahead of the voltage as they rotate. As they rotate. The voltage graph, PAVM, is a pure sine graph. The voltage graph, as you can see over here, is just a pure sine graph. But the current has already reached its values much ahead of the voltage graph. So the current is leading the voltage by 90 degrees. Is that absolutely clear in your head, guys? Let me know quickly in the chat box. Is this first point clear, why the current is ahead of the voltage? Yeah, phase difference is there. Yep, ahead by pi by 2. Who? Current. Okay, that was the first thing which we got. Now the next thing. You will notice that I did some manipulation here. Wondering, sir, why on earth will you do that? I'll tell you why I did it. Let's forget everything else. And let's just only concentrate on these. This and this. My current is nothing but my maximum voltage divided by 1 by c omega and multiplied by whatever that sine of omega t plus pi by 2. Okay, let's just forget everything else. Let's cut the noise. Now compare both of them. Immediately you will start noticing that this is my maximum current, I naught. So who is my maximum current? I naught is nothing but the maximum voltage divided by 1 by c omega. 1 by c omega. Let's reshuffle it. You will get 1 by c omega multiplied by I naught is nothing but V naught. This is what you are going to get. V naught will be I naught into 1 by c omega. Why I am doing this? Always in Ohm's law, voltages are currents multiplied by resistance. So dimensionally, if you look at it, if this is the dimensions of voltage, this is the dimensions of current, what will be the dimension of 1 by c omega? Quickly answer in the chat box. Won't it be the dimensions of who else? There is only one thing, V is IR. It has to be like a resistance. It has to be similar to the resistance. There is a problem. What is the problem? How can capacitor give resistance? You are absolutely correct. Capacitor cannot give resistance because resistance causes heat loss. Energy loss. Capacitor never, an ideal capacitor, purely capacitive, cannot cause heat loss. Rather, it stores the energy between the electric field of the plates. So, if it has to store, give it back during positive, negative cycles, it will get charged, discharged. So, it cannot be evil like a resistor who causes that loss. But there is one quality which is common, and that is it opposes the current. Because if this value goes up, current will reduce. So one quality is same, which is opposing the current, but, and also the dimensions, of course, and units. But what is not the same? Heat wise or energy wise. It is not causing any energy loss. So it will be not right on our part to call it resistance. Because capacitor will feel bad that you are putting me in the league of resistance, which is causing energy loss, and capacitor will cry and tell you, bro, what did I do so wrong to you? Okay, I oppose the current. Okay, my dimensions are same, but at least I did not cause energy loss. So at least don't call me resistance. You can give me a similar name, but don't call me resistance. Getting my point? Everyone? So what do we call it? We give it a new name and we call 1 by c omega It is like resistance, not the resistance. I call it XC. It is called capacitor's resistance, which is called as capacitive reactance. Reactance. So now capacitor is very happy. I got a new name. At least I'm not like a resistor. I'm not like energy loss machine. Okay, I oppose, I have same dimensions, but I do not cause energy loss. So reactance never will cause that energy loss. Is this concept clear? This is called capacitive reactance. So I can call this as XC. So I into R formula is still valid. V is IR. Look at it. V is nothing but I into R is still valid, guys. Just that the capacitive reactance is 1 by C omega. Is this now clear, the concept of reactance? Yeah. Unit obviously is ohm. Unit is obviously ohm. There is no energy loss in it. There is no energy loss in it, but it opposes current. It opposes, it opposes the current, of course. It opposes the current. That quality is same. Perfect. Clear? I'm pretty sure nobody would have explained you what reactance is. You would have just given the formula and like, okay, compare, and that is reactance. This is the true reason why it has a different name. Now that we know what reactance is, what the unit is, what it does, and what it doesn't do, you might be wondering, sir, you know what? Omega is there. For the very first time, resistance depends on the frequency now. A normal resistor was just dependent on the material, area, etc. But now, how much will it oppose depends on the frequency. Imagine if omega is very high, AC current is oscillating. What will happen? Denominator will become very huge. If denominator becomes very huge, the ratio will become very small. The reactance will also become very small. So if the current is oscillating very fast, thousands and thousands of hertz, then the reactance will be negligible, meaning huge current will flow in it. But if omega is very small, the denominator is going to be very big, sorry, very small, and the ratio will be very big. So reactance will be very big. So it will oppose a lot of current. And that's why when the current is changing very slowly, coolly, it's taking its own sweet time. After one day, it is changing the direction. Gone only. It will like, bro, I'm going to block you. Bro, I'm going to block you. So it is going to block such a slow moving current. So can I say very high frequency is being filtered and it is being given by the current, capacitor, but a slow moving AC current is being blocked by a capacitor. A slow frequency AC is blocked by capacitor, but a high frequency AC is allowed. That is what I can say. So high frequency versus low frequency. This is allowed, this it likes, okay, and this it blocks. So high ohms, this will be having low ohms of reactance. That's the logic of it. Yeah. Okay, perfect. So, my dear students, yep, same thing is there over here also in theory. The capacitor gets fully charged, discharged, the current, AC supply given to it, it continuously gets charged and discharged. So, current truly is never becoming, zero constantly. So, the charge also never stays. So, capacitor will stop DC current, but it will allow AC current. This is very important. This slow moving current is like DC only, barely changing. So it blocks it, but it allows AC current. Okay. So fast moving AC is allowed. A slow moving AC almost is like constant current. So then it will not like it, it will block it. And of course, we have seen the graph aspect as well. It's time to do some questions on it. Just see if you can do this particular question. Yeah. No, William, no new batches are coming. If you want, you can join the old batches only. Yeah, you will miss few things, but at least you will get the other things live. So the Sigma Crash batch is still there, man. Okay. So capacitor is given, EMF is given, maximum current is approximately how much? So if it is a capacitor, there will be a reactance. So there will be XC and multiplied by your current will give me the voltage. So my voltage maximum value is basically 36, okay, will be equal to XC, which is having a formula of 1 by omega C. This is basically omega. So 1 divided by omega, which is 120 pi, multiplied by capacitance. Capacitance is 150 micro. So 150 into 10 to the power negative 6. And finally, I will get the current. So solve this and you will get the answer. You have to multiply all these things. So 36 multiplied by 120 multiplied by 3.14 multiplied by 150 multiplied by 10 to the power minus 6. So whatever answer you get, I think 2 amperes roughly. Yeah, you should get, yeah, exactly the same thing. So you should get the answer close enough to 2 amperes. Okay, method is important. This was a calculative question which was given in 2024. Yeah, it will take your time, but yeah, it is simple only. Voltage is current into resistance, Ohm's law like equation, but resistance will be reactance now, which is 1 by omega C. Sir, if that is the scenario for your capacitor, can you tell me what will happen for an inductor now? It will be exactly opposite, man. You should have guessed it by now. Yes. No, there is no new Sigma batch, man, now. It's over. The Sigma entry is over now. So if you want, you can just join the last Sigma batch, which was there, you know, in the end of November or December first week, whatever. Okay. So if you take an inductor, what is an inductor? Inductor is based on the Faraday's principle. It opposes any changes in current and flux. So if you take an inductor, then it is connected to DC circuit, then it allows the current. It is very happy with DC actually because it doesn't like any change. Capacitor was exactly opposite. If you pass DC, capacitor are like, bro, what are you doing? You're not changing only. I don't like you. Inductor is not like that. If you don't change, capacitor, inductor loves you. Constant current is always maintained. Any changes in flux happens, that's it. Inductor will not like it. So inductor will actually block AC current as much as possible. DC current, it will allow. It's exactly opposite of a capacitor. So when you think of a purely inductive circuit, you will see that the graphs are also exactly opposite. Here, the current will be behind the voltage. Yes, current will be behind the voltage of the inductor. Okay, so voltage will be ahead of the inductor by 90 degrees. If you remember, for a capacitor, try to see the same thing. This is for an inductor, right? For a capacitor, current was ahead of the voltage. So it's exactly opposite for an inductor, guys. It is exactly behind. Now, what happens in case of an inductor? Let me also mention that. So same logic, if you have to use Kirchhoff's voltage law only again. So you have to use Kirchhoff's voltage law starting from a point and come back over here. And then you will see that if my current was I naught sine omega t, then my voltage will be V naught sine omega t plus pi by 2. So there is a plus pi by 2 in voltage. There is a plus pi by 2 in the voltage. So you will see voltage will be ahead, or you can say current has minus pi by 2. It's one and the same thing. Okay, however you want to do it. Now, if you do the math and you compare it, you will notice that again you are going to see the voltage across the inductor is the voltage of is the current passing through the inductor multiplied by a number which is omega into L. Now, think logically, guys. If something like this happens, what will you do? Voltage is current multiplied by a dimensional quantity similar to resistance. So this is also having unit of ohms. If this increases, current decreases, so it opposes, but it can never cause energy loss. Inductor stores the energy in magnetic field. Keep that in mind. So this will then become XL. So this XL, which is omega L, is called inductive reactance. Inductive reactance. Obviously, the unit is still going to be in ohms. It obviously opposes the current, but the only thing which it doesn't do, it doesn't cause loss of energy. Loss of energy. It stores it faithfully in its magnetic field. So that's why it is injustice to an inductor to be called a resistance, because it is not exactly similar to it. So you give a different name and keep it happy. So inductive reactance is omega L, and the voltage, just like Ohm's law, is V is I into reactance of that inductor. Okay, clear? And yes, the graph is ahead, so that is also similar thing. So let's have a look at it. 1 second, guys. Keep solving this. Okay. Let's do this question, guys. AC source, voltage is given, pure inductor, inductive reactance is how much? Inductive reactance is omega multiplied by L. So omega is basically this. So 628. Inductance 5 millihenry. So 5 into 10 to the power minus 3, guys. Come on. Yeah. How much is it coming out to be? Yes, 3.14 ohms. Are you getting 3.14 ohms? Because this should come close to 3140 into 10 to the power minus 3. And this is nothing but 3 powers, or 3 decimal places, 3.14 ohms. So that is what it should be. Okay. So this is something like, you can say, 0.5 means half. So half of 628 is 314. So, it is 3140. Simple. So 3.14 ohms. That should be the answer. Just check it out. Yes, perfect. Simple, straightforward. If reactance is known, we can also find the current. It is not asked, but I'm just saying, if current was asked, maximum current, it will be the maximum voltage divided by the reactance. So maximum voltage will be 260 and the reactance will be 3.14. So this many amperes will be the maximum current if it was asked. But it is not asked now, so I'm just showing it to you. There was one more question which was asked in the JEE examination in 2024. There was a graph given of reactance, and the graph was a curve A and a straight line B. And one of them is XC, one of them is XL. Given the horizontal line is the frequency. They wanted you to identify which graph is which. And maybe one of them could be resistance also. So they were just asking which of these curves represents what. So we know for inductor, it is omega L. That means it is 2 pi f into L. That means it is proportional to the frequency. For XC, it is 1 by omega C. So it is 1 by 2 pi fc. That means it is inversely proportional to f. And resistance is independent. It is always a constant. So it becomes obvious now that my curve A, it is inversely proportional. So this curve must be for a capacitor. And this particular straight line where it is proportional to F, this must be for an inductor. So B stands for inductor. So B stands for inductor and A stands for capacitor. A stands for capacitor, so it should be option C. Yeah, can you see that? It should be option C. What is Z? Don't worry about it. Impedance and all that, we'll come to it in the next part. But you don't need to know about impedance also even to solve this question. Yeah. So the answer for that is C option. Okay. CBSE board exam, yes, it will come, my dear. Don't worry. So now that we have learned inductor, resistor, and capacitor separately, we are going to combine all of them together. But before that, let's take a quick break and return. Okay. So it's time for a break. So we'll just have a dinner break and return. Okay. Cool. Welcome back, guys. I hope I'm audible and visible to all of you. Hi, Louis. Hi, Hogwarts. Sabri. Yes, everyone. Am I audible, visible? Yeah, it's time to continue the class. LCR circuit in series and power in it, and then finally we'll go to transformers. That's the only part which is remaining. Okay. Yeah, but this is very interesting because now we are going to use all the knowledge together. We learned about RMS, maximum, omega, then we also learned about phasors, then how current might either be behind or in sync or ahead of the voltage in case of resistor or capacitor or inductive circuits. And every time Ohm's law is valid, V is IR, but that R will keep changing. For a resistor it is R only, for capacitor it is 1 by omega C, and for inductor it is omega L. They are called reactances instead of resistance. That's the only difference. At the end of the day, everything is voltage is current into either a resistance or a reactance. So the reactance could be inductive or capacitive, right? Till this point, I think everything is clear. So it's time to now, okay, to see what happens when all the three of them are together. Okay, all the three are good. Yeah, together. Now, say for example, this particular scenario, you have a circuit in which all the L, C and R elements are there, and there is a current which is passing through it. Let's say it is I naught sine omega t. That is the current passing through it. There is a total voltage across the entire circuit. I will call it V. This is the total voltage. This is the total voltage, which is also going to be a function of time. Okay, this particular voltage is going to be a function of time. There will be also voltages across the inductor, capacitor and resistor separately. They are in series, same current will flow. So there is a voltage across the inductor as a function of time, voltage across the capacitor again as a function of time, and voltage across the resistor again as a function of time. But since they are in series, I can say that current, the same current of I, which is I naught sine omega t, will flow, will flow through, will flow through all the three elements: inductance, capacitance, and our resistance. This is the first point which you should realize because they are in series. But their voltages are different. So using our simple Kirchhoff's law, or just the total voltage will be the sum of the voltages, I can just say the total voltage at any given instant will be the voltage across the inductor at that instant plus voltage across the capacitor at that instant plus voltage across the resistor at that particular instant. Is this absolutely clear? So the voltages, if this is 3 volts, this is at some instant, okay? This is 1 volt, this is minus 5 volts. So 3, 1, minus 5 together will give me whatever is the total voltage in that circuit. But keep in mind, each of them are functions of time. They will be sine, cos, etc. So if you think about it carefully, inductor, go back. Inductor, what happens? The voltage, yes, the voltage is ahead of the current by 90 degrees. For a capacitor, it is behind it. So we have seen this over here. So for an inductor, the voltage is ahead of the current, whereas for a capacitor, the voltage is behind the current. The current was here, voltage was behind. So if that was the logic, then I can just say, if I compare it with this particular current, it will be something like the maximum inductive voltage VL naught, because it is going to be ahead. So sine omega t plus pi by 2, number one, plus voltage across the capacitor is always behind the current. So VC naught. VC naught is the amplitude. VL naught is also the amplitude. So naught stands for the amplitude of that voltage or current into sine omega t minus pi by 2. And lastly, for the resistor, it is simply in phase. So it will be VR naught sine of omega t. That's all. This is how that function will look like. Each of them are functions of time, but with respect to the current, voltage across the inductor is ahead. With respect to the current, capacitors is behind. With respect to the current, resistor has the same phase. So there is no plus or minus over there. And what about this? This voltage? Well, that will be something like V naught sine. I don't know what the phase is, so I'm just going to put a phi over here. So this is my final equation as it is at any given instant. I do not know what phi is, and maybe I might know few of these things. From that I can find V naught. This equation is a just simple algebraic addition of the instantaneous values of time. Now if I ask you, if this is the equation, will V naught be equal to, will V naught, the total amplitude of the voltage, will it be equal to the amplitude of the voltage across the inductor plus amplitude of the voltage across the capacitor plus amplitude of the voltage across the resistor? Will it be equal? The answer for that is obviously a no. This can't be true. Obviously, this can't happen because there is some sine and cos terms in between. Whenever you have such things in mathematics, where you see this is sine, cos, etc., and they have to be added, this is like superpositioning of SHMs or superpositioning of wave-like functions. And whenever you do superpositioning of waves or SHMs, it is essentially a vector addition of their phasors. It is nothing but a vector addition of their phasors. So instead of doing all of this, I can say, instead of doing all of this, I can just say, I can take the phasor of the nodal voltage. I can take the phasor of the inductive voltage. I can take the phasor of the capacitive voltage, phasor of the resistive voltage, and then I can add them. And then I will see that vector wise it will be equal, but not the scalar number. But not, I think I erased it by mistake. Second, I'll just do it again. Duplicate. So not there. Okay, I will write it down here only. But whenever you have wave-like functions, you can take the phasors, and this will be equal to basically VL naught bar plus VC naught bar plus VR naught bar. These are the phasors. So phasors which are treated like vectors and being added to give you the net value. This is allowed. There is nothing wrong in this. So what happens then is that if I draw a phasor diagram, say for example, this is my current phasor. Okay, this is my example current phasor over here. I will call it I naught. With respect to that, the voltage across the resistor will be in phase of it. So I'm just going to put VR naught like this. Voltage across the inductor is ahead of the current, so I have to show it on this side. So it will be like this, VL naught. And voltage across the capacitor will be opposite of it, like this, behind the current. So VC naught will be like this. This is how the phasor diagram will look like for the LCR series circuit with all the three elements. Till this point clear? Why I'm showing it like this? Now, because in order to find the net voltage, I have to take their vector sum. What I will do is, okay, I will first deal with these two vectors because they are opposite of each other. So if I take this vector and this vector, assuming this is small, this could be big also, doesn't matter. So first, if I deal with these two vectors, I will get a vector of so much height like this, and the length of this particular vector, this minus this, if I do it, okay, I will get this as lengthwise VL naught minus VC naught. The resistance voltage is still going to remain as it is. So this will be VR naught as it is. Now I have two vectors which are mutually perpendicular to each other. So if I want to find the resultant, obviously I just draw this line using parallelogram law, and this is basically going to be V naught. This is essentially going to be V naught. Is this clear, guys? How we got the resultant voltage from the individual amplitudes of the voltages across the elements, inductive, capacitive, and reactive. These are SHMs which are being superimposed, different SHMs to give you a resultant SHM. Whenever SHMs add, you take the phasor quantities, not their scalars. You take the phasors, treat them like vectors, and add their amplitudes with the right direction. The direction is very important, or else you will get a wrong answer. So, if I take first current, because current is the same, that is the reference, then resistor is going to be in phase, inductors will be 90 degrees ahead, capacitors will be behind, and then you take the addition of these three vectors, I am going to get this. Isn't it perfect? So now what will be the value of V naught? The value of V naught by Pythagoras theorem will be this side square plus this side square, the whole thing under the root. So I'm just going to put a big root over here, and I will say it is nothing but VL naught minus VC naught the whole square plus VR naught the square. So this is the correct expression, not this. So I cannot just add them. It's meaningless. I can't just add their amplitudes. But if I take the proper directions and I use geometry, then geometrically, this is what I'm going to get. So this is the right formula, guys, for voltages. Absolutely clear? Okay. Even this you should know that you can add them like phasors. You can add them like phasors or vectors. You can add their instantaneous values also. But you cannot add their maximum values because they don't reach maximum together. Keep that in mind. Their maximum values are not reached together. Now, once I get this, I get another idea. What idea you got, sir? I'll tell you. Actually, I don't need this. Okay. Just create a duplicate. Okay. Sir, if I square both sides now, what I will get is V naught square is equal to VL naught minus VC naught whole square plus R square. This is what I get. I'm just squaring both the sides, so the root goes off, so V naught square will be here over here. Now, what is VL naught technically, or what is VC naught, or what is R? Sorry, why did I put R over here? Remember, this was VR naught. It was VR naught whole square. See, guys, VR naught, VC naught, VL naught, all these things will be always the maximum current, which is I naught, multiplied by the respective resistances. Like for resistance, this will be R. For capacitor, this will be XC. For inductor, this will be XL. Ohm's law, V is IR, V is IR, V is IR. So maximum voltage is maximum current into reactance. Maximum voltage across capacitor is maximum current into capacitive reactance. Maximum voltage across resistor is the maximum current into its resistance. Simple Ohm's law. This is still valid. So let's use that over here and see what do we really get. So we are going to have over here, I think, let's just put equal to V naught square as it is, VL naught, VC naught, and VR naught. Everything has I naught square common, if you notice. So I'll have I naught square over here, and inside the brackets, I'm going to have XL minus XC whole square. And over here also, I'm just going to have I naught square over here, and I'm going to have R square. I can definitely take I naught square as a common entity. So this will come outside, and then inside the brackets, I will have XL minus XC whole square plus R square. Okay, I have taken it common. Now take square root on the both sides and see what do you get. So V naught will be equal to, observe this, I naught, and this thing will be under the root, which is XL minus XC whole square plus your R square. Now again compare it over here, guys. You want to see one fantastic thing. Voltage is current into resistive element every time, resistive or inductive. Here also voltage is current multiplied by the dimensions of resistance. And if this quantity is higher, current will automatically go down. So again, I have something like a resistance, but not exactly resistance. Plus, I cannot even call it reactance. Why I can't call it reactance? Because reactance is only when you have inductor or capacitor where there is no energy loss. Resistance causes energy loss. It's a combination of energy loss and a combination of no energy loss. So if I call it resistance, then these people will feel bad. And if I call it reactance, then I am being lenient with the resistance. How can I call this entire thing reactance? Because reactance was a privilege to only such elements which oppose current but do not cause energy loss. So neither do I have the privilege to call it reactance, nor can I be, so strict and call it resistance, because then these people are going to feel bad that how can I be put in the zone of resistance. So then I'm like, okay, don't worry. If you two are together, then I will introduce a new term and I will call it impedance. And I will call it impedance. And the symbol for that is no longer X. Again, I cannot use the same symbol. So I will use a new symbol, and that is basically Z. That is basically Z. So same things here and here also, as you can see. All these are basically Ohm's law. Even this is also Ohm's law, as you can see. Just like Ohm's law. All of these. And this particular Z, which is also called as impedance of the circuit, is the total resistance of the circuit, including reactance of capacitor, inductor, resistor, everything. So that is your Z, and that is obviously equal to XL minus XC whole square plus your R square. So I can block this. Obviously, unit is still going to be Ohm. Unit is still going to be Ohm. It will reduce the current in the circuit, obviously, but it will also cause energy loss. It will also store some energy in magnetic and electric field. All those things are there. It's a combination of both of them. Okay, I hope you understood how Z comes, everybody. Now looking at this diagram, one more thing should click in your head. You can even draw resistance as a vector. Yes, even you can draw resistance as a vector, meaning if this is my current phasor, and the resistance of a resistor as a phasor will be in line with the current, because the voltage across the resistor is in sync with the current. So same privilege I will give it to the resistance also, and then I will show XL over here, and I will show XC over here, just like I have shown this particular diagram, VR naught, VC naught, VL naught. I can show this particular diagram. Now, if I deal with these two quantities first, I will be just left with the term XL minus XC, and I will just have horizontally, I will just have resistance, and the total combination of both of them or all of them together, I'm just going to get the term Z over here. And you can see again by Pythagoras theorem, This Z will be obviously XL minus XC whole square plus R square. Same thing. Pythagoras is still applicable over here. In fact, this was also very natural. I'll tell you why. If you take this elements and multiply with I and I. What is this IR? It will be voltage across a resistor. This will be voltage across capacitor. This will be voltage across inductor. So it's basically you are increasing the dimensions I times. If you multiply this I times, you are just going to get exactly this, nothing different. So if I shrink this I number of times, I am just going to get the resistance phasor diagram. Getting my point? Yeah. I'm going to come to resonance later on. Hold on. Yeah. Resonance in a bit. But for now, I hope this much is understood. Now, lastly, I have also figured out what is the final phase. Remember, the final phase of the net voltage was also important. That phi is right over here. So, this is phi. You can use any of trigonometric ratios. For example, tan of phi will be opposite side, which is VL naught minus VC naught, whole thing divided by VR naught. This is also fine. You can also do the same thing over here, where again, this is also fine. And you can still say tan of phi will be opposite side, which is XL minus XC, whole thing divided by the adjacent side. Anything works as long as you are, using your basic principles of geometry. It's fine. It's the same thing. So tell me one thing. In this whole thing, I feel there is not a single formula that you should remember as such. I mean, okay, this is there. Where is it gone? This is there. Ohm's law. But Ohm's law, everybody knows voltage is current into resistance. Only the resistance is changing. Yeah, the names are different. But meaning wise, they are all resistance only at the end of the day. Even this total voltage is total current into total resistance. This is something which is very familiar. You are very familiar with. The only thing, even this formula I will not by heart, guys. I mean, not needed also, because I know everything is being added and treated like vectors. Whether it is voltage, if I know how it works, who is ahead, who is behind, I know even the resistance and reactances are also like vectors. So technically, it is simple geometry. I won't even remember this formula. If I know, okay, XL is here, X is here, it is a beautiful triangle, I can use sine, cos, tan, anything. Where you will sit and realize, remember tan phi is how much, sine phi is how much, cos phi is how much. Needed. It's just simple geometry at the end of the day. Okay. Is this clear, everyone? So impedance done, reactance done. What is it? All of these things are done. Same things are given over here also, here also, here also, here also. All right. Now that we are done with this, let's come to an interesting case of resonance and also the two other sub cases. Say case 1 and case 2. First case where XC is more, case 2 where XC is less than XL. Meaning, imagine a circuit where the capacitive reactance is less, inductive reactance is more, inductive reactance is more. So what will happen? The net impedance is going to come like this somewhat. This is your current and this is your phi basically. This is your impedance. This is your current. Yeah. This is how it will look like. Such a circuit which has more of XL than XC. The vector on the top is bigger than the vector at the below. That is said to be inductive circuit. Okay, because XL is bigger in value. But the exact opposite will look like this, where you have, okay, again, let's say the current phasor, and then all the other things. XL is smaller, XC is bigger. So the net vector will come like this. This will be your impedance. This will be your current. And you will see the phase angle will come below like this. And by the way, even the net voltage, if you draw it right, the net voltage will also go like this only in the same diagram, in the same direction. Yeah, in the same direction. Here the net voltage will be like this. This is your net voltage. Here, this is your net voltage. So your voltage is behind current. It is then said to be capacitive in nature. Okay. If voltage is ahead of current, then XL is more, then it is said to be conductive, inductive in nature. Okay. Are these two variations clear? When XL is more or XC is more. Now, how XL and XC are changing basically? How does XL and XC change? If you think about it closely, how does XC and XL change? We all know XC is nothing but 1 by omega C and XL is nothing but just omega multiplied by L. These can change if frequency changes. So the source, the AC source, if the frequency changes, these quantities will change. Accordingly, they will adjust themselves here. Accordingly, XL can be more or XC can be more, any one of them. So, can you see there is one particular situation which is arising now where both of them will be equal? Where essentially both of them will be equal, XL and XC both are equal. So, in that situation, how will the phasor diagram look like? How will the phasor diagram look like? XL, XC, resistance, you will also see current may be like this, and even the total voltage will be like this. Everything will be in this manner. So this will be total voltage. This will be also the impedance, by the way. This will be the total current. There is no phase angle. Such a situation is said to be resonance. Okay, and when resonance occurs, you will see maximum current will flow in the circuit. What happens is these two are equal. No? When these two are equal, think about it, the impedance will go down. Why will the impedance go down? Check it out over here. There is something square plus something square under the root. So just imagine if I were to calculate impedances in the first situation, let's say it is root of 5 minus 2 whole square plus this is 7 square. Then second time the impedance is, example, this is 4 minus 3 whole square plus 7 square. And third time it so happens that it becomes 3.5 minus 3.5 whole square plus 7 square. Now tell me, out of these three numbers, who is the biggest, who is the smallest? It's obviously this is the maximum value, but I'm not interested in max, I'm interested in minimum. This is the minimum value because this over here is becoming 0. So I'm not adding anything to this. Otherwise, every single time, whether it is 4 minus 3, 3 minus 4, doesn't matter, it is squared, it will be a positive number. So I'm adding something, so this value will be larger. Yeah. So what happens because of that? What happens because of that? When Z is minimum, try and think about it. Our total voltage is nothing but the current multiplied by the impedance. So if Z is less, for the same voltage, my current will be highest. My current will be obviously the highest. So that is the logic behind it. So what happens now, if I go down over here, that's exactly the concept of resonance. When these two numbers are equal, right, XL and XC are equal, you will notice the current is maximum, impedance is minimum because XL and XC are equal, and more than this you cannot have current, and less than this you cannot have the impedance. Bare minimum, at least that much will be there. If you see, this will become 0. So root of 7 square, that is just going to be equal to 7. So that's why the impedance becomes the resistance. The impedance becomes the resistance. That's why over here I have shown Z exactly matching with the resistance. Earlier Z was at an angle with the resistance. Z was at an angle with the resistance. Now it is no longer at an angle. It is the resistance also. So Z is actually equal to R. Think about it. Z is actually equal to R. So if you draw a graph of the impedance for a LCR circuit, the impedance will shrink, become least, which is R, and again after that it will go up, and exactly at resonance it is the least. And the exact opposite graph will be there for your current. Exactly opposite graph will be there for your current. So this is F. Let's say this is the current over here, and the current graph is going to look something like this. This is the maximum current. This is nothing but I naught max which you can get, and this happens at exactly the resonant frequency. You can call it F naught or Fn, whatever you want to call it. Okay, so maximum current at resonance. Now I'm interested how much is that resonant frequency. It is not that difficult to figure out, since we already said that XL will be equal to XC. Even by the way, also you will notice at resonance VL will be equal to VC, and the total voltage will just be VR. Yeah, these two will essentially cancel each other out, and the net voltage will be just the voltage across the resistance, nothing else will remain. So now if you do the math, it's straightforward. XL is nothing but omega into L. This is XC. XC will be 1 by omega C. So omega into omega is omega square, will be 1 by LC. Therefore omega will be 1 divided by root of LC. So now take omega is 2 pi f. You can also call this as omega naught, which is the resonant frequency, not any random frequency. So 2 pi f naught is 1 by root of LC. Therefore, resonant frequency will be 1 divided by 2 pi root of LC. So this formula or this formula, anything you can remember. Usually people remember this because this is more convenient. So the natural or frequency at which the circuit will resonate, angular frequency wise, is 1 by root LC. Hertz wise, this is the answer. So at this frequency, maximum current will occur, or least impedance will occur. One and the same thing. Okay, cool. I hope this is absolutely clear. So same thing is there in these diagrams as already suggested. Okay, perfect. So we are done with LCR circuit. So we started off by discussing how voltages get added at any instant, but you cannot add their amplitudes. But yeah, you can treat them like phasors. And when you take phasors, then you take vector addition of their amplitudes, and you can use trigonometry, geometry, Pythagoras, and same thing can be also applicable for resistors also. And then we saw that how resonance occurs when both inductive and capacitive elements cancel either their voltages or their resistances. There is no phase difference. Impedance is minimum, current is maximum. And this is the frequency at which resonance occurs. All right. So it's time that we do some questions coming up on your screen. And here it is. Well, we have this question. There is an AC circuit which undergoes electrical resonance if it contains either capacitor or an inductor. An AC circuit containing a pure capacitor or a pure inductor consumes high power due to its non-zero power factor. Oh, we have not yet discussed power factor. We should come to this question later on. Hold on, we'll come to this later on. Okay, first let's do this question. In the LCR circuit, the EMF is E, current at resonance is I naught. If the value of resistance becomes twice of its value, then what will be the current amplitude at that particular, new resistance? That's the question. Okay, so what will be the new maximum current? All right, let's figure this out. When you are in resonance, we know that the impedance is equal to the resistance, and the total voltage is the current, maximum current that I will get, multiplied by the impedance. But the impedance itself is resistance, so I'll just put R over there. So E is equal to I naught into R. Now in the second scenario, when the resistance is doubled, now resistance is doubled, but EMF is the same. So I will have 2R and I will have new maximum current. I will call it I naught prime. So comparing the two, if this is basically your I naught prime multiplied by 2R, the EMF is the same. So it is I naught R over here, RR cancels. So it's kind of obvious now. I'm getting I naught prime as I naught, the 2 goes below, divided by 2. So I naught prime is basically I naught divided by 2. Yes, that is option number A. Got it? So the maximum current will reduce. There is no question of capacitors or inductors in this question. It will just behave like a regular resistive circuit now. Because if you look at the phasor diagram also, I mean, it is quite obvious. Look at the phasor diagram. The voltage is in phase with the current. There is no phase difference. So it feels like a regular resistive circuit. V is IR. So all resonance circuits are like resistive circuits. There is no net inductance or capacitance. Okay, that's the beauty of resonance. All right. So this was done. Let's go to the next question on your screen. In a LCR circuit at resonance for a capacitor, inductance and this thing, value of resistance is half, keeping all other parameters same. The current amplitude at resonance will be now. Oh, interesting. So the current amplitude will be what? The value of resistance is half, keeping all the parameters same. It's just like the previous question, if you remember, where you had that net voltage is the maximum current multiplied by the resistance. So if somebody decides to take this resistance and make it half, it is quite natural to keep this particular entity constant. To keep this constant, this current will have to be doubled. So their product will be constant. So hence the answer should be D. Yes, it is doubled. Yes, D for IIT Delhi. Perfect. Amazingo. Amazingo. Kudos to all of you. Very good. Let's go to the next question coming up on your screen. So you can see most of the questions are usually on resonance. All right. In a series LCR circuit, the capacitor is changed from C to 4C. To keep the frequency unchanged, then the new inductance should be how much? The resonant frequency, omega naught, is 1 by root of LC. It is clearly mentioned that this is still the same. So the product of these two should be the same. So if capacitance is made 4 times, it's quite natural the inductance should be made 1/4 time. So it has to be 1/4 of the previous one. But understand, the old inductance is L. The new inductance is L by 4. I think that's why this is a JEE question. Lot of people will write option B, that is wrong. So it has to be reduced by, it has to be reduced by how much? 3L by 4. Hence, C option will be correct, I believe. Yes, not B option. It is not what is the new inductance. It is how much will you reduce by. The new inductance will be reduced by C option. Yeah. Is this question absolutely clear? Yeah. Perfect. Okay. Awesome. Awesome. I will give you one more question. All right. All right. Same thing is there over here also. All right. I'll give you one more question over here. Example. It is given to you that XL is 7 ohms. XC is 1 ohm. Resistance is 8 ohms. The AC source, all right. So it has a voltage of AC source, let's say it has a voltage of 141 volts. 141 volts. This is given to you. Question is, find number one, impedance. Number two, phase difference between voltage and current. Number three, what is the maximum current amplitude? Okay, what is the maximum current amplitude? I think that should be more than enough. Yeah, I think you have figured out then everything literally. So that is the question. Okay, so let's try to figure this out. First things first, XL, XC and R are given. So finding impedance is not a big deal. So what do you need to do for finding the impedance, guys? Yeah, just have to take the formula Z, remember, or you can use Pythagoras also. XL minus XC whole square plus R square. Okay. So XL is nothing but 7, XC is 1, R is nothing but 8. So square it. 7 minus 1 is basically 6. So 6 square is 36, 8 square is 64. So this is going to be 100. So this is basically going to be 10 ohms. So impedance we have found out to be 10 ohms. That part is done. How many of you got the impedance as 10 ohms? Very good, Sabri. Amazing. Next important thing. Phase angle is asked. So for that, I think better to have the phasor diagram. It will be easier. So resistance will be like this, and XL minus XC will be remaining like this. Remember, actual value of XL will be larger. Actual value of XC will be over here. But if you take the difference, this will be XL minus XC. This will be just the resistance. And then I'll get the total impedance from here. So now I want to find what is the phase angle. Therefore, tan of that phase angle will be XL minus XC divided by the resistance. So XL is how much? 7. XC is how much? 1. Resistance is how much? It is 8. So this will be 6 by 8, which is 3 by 4. This is a standard angle, guys. It is nothing but 37 degrees. So phase difference is 37 degrees. And do not forget that this will be also the direction of the voltage, and this will be the direction of the current. So voltage leads the current by 37 degrees. Voltage leads the current by 37 degrees. Okay, that also done. Now comes the last part, which is the current. For that, we know one simple equation, which is the total voltage is maximum voltage is total maximum current multiplied by the impedance. V is IR. You can use it for anything. So Z, I know already. I naught I have to find, which is what is the question. Voltage 141. This is what many students make a mistake over here. Be careful, guys. This voltage is the maximum voltage, but whatever is given over here, don't be confused. This is actually RMS voltage. When nothing is specified, remember it is always RMS. So maximum voltage is technically root 2 times RMS voltage. This is I naught multiplied by Z. So therefore, this is a very common mistake many kids do. RMS is 141. I naught, I have to find that out actually. And Z is basically the number 10. Now 141, guys, this is a standard thing. So this is nothing but root 2, which is 1.414, but you multiplied 100 times. So if you want to write 141, it is 1.41, yeah, multiplied by 100, which is root 2 into 100. So I can just write it down like this. So root 2 into root 2 is 2, multiplied by one of the zeros gets cancelled, it will be I naught. So therefore the current will be 20 amperes. But this is, remember, the amplitude of that current. If RMS is asked, then again I have to divide it by root. That's all. Understood? Clear how to solve these kind of questions? It's at the end of the day vectors, addition, nothing more. Okay, so it becomes easy once you understand the concept. Cool, guys. Now let's go to something called as the power factor, guys. Power in the AC circuit. power in the AC circuit, and then we can also go back to the first question. So we all know, we all know that inductor L and capacitor can't lose energy, only R resistance can. Therefore, the power of a AC circuit is also the power only across the resistance. Power only across the resistance in AC. But there is a problem. How do I find the power loss across a resistor? Because the current is continuously changing. Exactly for that, we created the concept of RMS so that we don't have to break our head every single time integrating or differentiating. I can just say the power across the resistor in AC is nothing but the power across the resistor in DC considering RMS value, DC RMS value. So what is that RMS value of that particular current? I will just write IRMS of that thing square multiplied by the resistance. So this is exactly the power loss in a AC circuit. IRMS square multiplied by resistance. There is no L, there is no question also of C. It doesn't come only. It's just RMS value of the current into square into R. That's all. And not to mention, this same RMS current will be also maximum current divided by root 2. This will be also maximum current divided by root 2. Very straightforward. But you can play around with this. And how do I play around with this? I will just write it down as simply VRMS, sorry, not VRMS, IRMS multiplied by again IRMS, but that I can write it as VRMS divided by Z multiplied by R. Why am I writing it like this? Because this quantity which is there over here, IRMS, current is voltage divided by impedance. So that square I wrote it 2 times, but one of those IRMS I have written it as V by Z. That's all. Just reshuffle them. So it will look like this. VRMS into current RMS multiplied by R divided by Z. Now, why did I do it like this? The power loss in that AC will be VRMS into current RMS multiplied by, what is this R by Z, guys? Well. If you remember the resistance phasor diagram, resistance is like this, Z is like this, and this was your XL minus XC. This is how it was. This was R, this was your Z, this was your phi, this was your phi, and this was your XL minus XC. What is R by Z? Adjacent by hypotenuse. It is cos. So this is going to be cos of phi, and this is another way of writing the same thing. Instead of I square R, you can write VI cos phi, but all of them are RMS. Keep that in mind. Now this entity over here, cos phi, is only called as the power factor. This is only called as basically our power factor. Is this understood? What is power factor? Yeah, the cos phi value. So now I get an idea. Okay, I go back, where I discussed resonance. Yes, right over here. Interesting thing, whenever it is inductive or capacitive, there is a value of phi, but only when it is at resonance, phi is 0. And cos of 0 is 1, and that is the maximum value. Keep that in mind. So, when resonance occurs, since phi is 0, cos phi is 1. So, the power factor is maximum. So, there is maximum power in that AC circuit. So, there is max power in the AC circuit exactly at resonance because the power factor is exactly unity. Everything else like cos of 60, cos of 20, cos of 88 also will be lesser than 1. So maximum power, maximum current, least impedance, all good things are happening at resonance. Okay, so that is a very important thing which you should be aware of. So if I use that same concept in this particular question, which was asked in 2024, in an AC circuit which undergoes electrical resonance, if it contains either a capacitor or an inductor, and an AC circuit contains a pure capacitor or pure inductor, consumes high power due to its non-zero power factor. Now I think this problem can be solved easily. Tell me guys, option A says Sabri. Yes, perfect. Both are false. AC circuit has electrical resonance if it contains either a capacitor or an inductor. This is wrong. The answer should be not either, should contain both capacitor, and this word is also wrong, and an inductor. Because XL has to cancel XC. Only if XL is there, what will be there to cancel X? There has to be a capacitor. Only capacitor also can't exist. There has to be an inductor. So that's why both have to be there. So that is false. AC which has pure capacitor or pure inductor consumes high power. Think about it. If it is a pure capacitor or a pure inductor, what will be the value of phi? The value of phi in that situation will be either plus or minus 90 degree. And what will be cos of 90 degree? It will be obviously 0. So the power will be also 0. So that means this will be the least power. It will be the least power. Here it is said high power, which is obviously wrong. So both statements are incorrect. Yeah, if it is purely inductive, inductor never causes loss. Forget the formula, forget. Just think normally. Inductor, can it cause loss? No. Capacitor, no, it can store energy. Only resistor can cause loss. So anyways, even if you don't know the formula, you should be able to say, how can it be high power? It will be less power. In fact, it will be zero power, not even less, zero power. So that was the concept over there. So, all right, I think we can do some questions, but same theory is there over here also. I've put it up like this. Now, yeah, now there is one thing though, which I want to tell in power in a AC circuit. Okay. Say for example, I consider a hypothetical triangle like this. This is 90 degree. This angle is fine. Imagine the base of the triangle is VRMS, IRMS into cos phi. This is a hypothetical triangle. That's all. What will be the hypotenuse? If this is cos, this will be the main vector or main thing. So this will be without the cos. So it will be just VRMS into IRMS. That's it. Nothing else. So the cos component will be the adjacent side or the base. What might be the height? It will be the sine component then. So it will be VRMS into the RMS current multiplied by the sine phi. Now, this particular triangle that you are seeing, this is called as the power triangle. What is it called? It is called as the power triangle. It is called as the power triangle. Very good. Excellent. Excellent. Now, what happens when you have a power triangle? What is the significance of this? This quantity which you are seeing is actually the power which is there in the AC. It is the real power. So the base of this triangle is often called as the real power of that AC circuit. What is this then? This is the term which you will get if you did not have any knowledge of AC. You are a gugu, you are a dumbo, you are a fool. Imagine. And you don't know AC, voltage and current are in different phase. So the concept of phase is not even there in your head. So you will just multiply voltage and current. Power is VI, because that's what you learn in DC circuits. You will just multiply them and you will feel that that is the power. So when you feel something, that is called apparent. So that is why it is also called as apparent power. This is also called as apparent power. Lastly, what is this then? Okay, so surprisingly, this quantity ends up being that energy which keeps going back and forth between the inductor and capacitor. Remember, they never actually cause energy loss, but when inductor has maximum current, capacitor will have least current, and vice versa. So they will keep juggling their, energies. This will have electrical energy, then it will give it off, catch in magnetic energy. Then inductor will give it off to capacitor, hey, catch electrical energy. So they keep on juggling that energy between both of them. So that is also called as reactive power. Reactive because they are reactances. So reactive power, which is between L and C, they keep shuffling. They keep shuffling between L and C. It has not got anything to do with the resistance. Okay? Is that clear? Understood? This is the concept of power triangle, my dear students. Okay, perfecto. So, yeah, we have done all of this. This is also done. All this is same thing, guys. Power in AC circuit, all of these things, reactive power, active power, everything, power factor, everything is done. Okay, so let's do some questions based on this. AC voltage is there. It's applied to LCR circuit which drives the current. The average power is how much? How much is the average power? Very straightforward question. I want everybody to figure this out. Not that difficult. Average power dissipated. So the power in AC is VRMS, current RMS into cos of phi. But RMS current is maximum volt, or RMS voltage is maximum voltage divided by root 2. This is maximum current divided by root 2, and this is cos of phi. So what is maximum voltage? 20 divided by root 2. Maximum current 10 divided by root 2. Cos, which angle was there? Actually, if you see the phase difference, this is sine, so pi by 3 was there. So cos of pi by 3 means cos 60, which is basically half. Okay, so root 2 into root 2 is 2, 2 into 2 is 4. So this will become 20 multiplied by 10 divided by 4. So 20 by 4 is 5. So pi multiplied by 10. So that is going to give me 50 watts. Is that okay? So option D will be the right answer. Very good, Shreyas. Wow, my name. Hi, very good, Lewis, Sabri. Yes, Harish, amazing. Oh, perfecto. Let's go to the next question which was asked in your JEE 2024. Voltage is given, current is given, again average power is asked. I think again you can do the same thing. Same question is getting repeated again and again and again, guys. So nothing great. You will be easily be able to solve it. Now we can do it directly. Power in the AC will be maximum voltage by root 2, maximum current by root 2, RMS basically, into cos of the phase angle. So maximum voltage 100 by root 2, maximum current also 100 by root 2, cos of basically pi by 3. So 100 into 100 is 10 to the power 4. This will become 2. This will become half. So this will become 10,000 divided by 4, which is basically 2500 watts. 2500 of watts, but there is a catch. This is milliampere and this is volt. A lot of people might mistake that. So 10 to the power minus 3 will come. So here also, yes. So there is a power of minus 3. So there will be a 10 to the power minus 3, which will make it 10 divided by 4, which is 2.5 watts. So yes, If you miss that milliamperes, then you will miss this. So 2.5 watts, which is C option. There you go. Amazing, amazing. Simple. So these kind of questions are coming in your JEE mains examination. So just doing that. Now let's go to the last and final topic, which is basically transformers. Ready for transformers, my dear warriors? Yeah? Oh, Shreya ask. No, Shreya SK. Okay, okay. Yeah, because that SK is also there, no? Oh, and I can't read all the names very, very fast. And especially when you have these prefixes and suffixes. Okay, Cookie ready, Vamsi ready, Akash ready. My throat is paining, guys. Morning also I took class. My eyes are also burning now. But yeah, I will be taking the class. And I'm seeing not many students are also serious. They think that if I watch 1 hour class on AC circuit somewhere, my job will be done. Now you tell me, how can you learn a topic like AC in 1 hour? It's been almost like what now, 3.5 hours, and still we are on to transformers. Will take good half an hour now. So almost 4 hours it takes to at least understand the concepts and basic applications of JEE mains level for getting into that AC. Now after this you have to practice. Obviously that will take more time. So one shots is good for revision, those small ones, which we'll be doing on the channel, but don't depend on one shots for learning a concept, because that will half cook your brain. At least fully cooked is okay. Means you don't know anything. Okay. All right. Cool. If I study only important topics, which is for the yes, Shreya, you can do that. You can easily get 99 percentile. You will at least reach close to that, but you have to do all the important topics. You cannot leave 1, 2 important topics. In that, you cannot have choice. And every single important topics, you have to practice all models of question. Definitely you will get. Okay. Yep. I'm hoping on that cookie time. Now, this is a very beautiful diagram. I love this diagram, guys. It tells you how electricity comes to our homes, and you might have a good idea, but still, see, in a power plant, it could be nuclear, hydro, thermal, whatever, doesn't matter. The electricity is generated. There are magnetic coils which are revolving using Faraday's and Lenz's principle. So, magnetic flux changes and electricity is produced. Okay, fair enough. But like, okay, sir, why don't we just connect the wire? I mean, like, wow, what is all this nonsense? What is this thing? What is this thing, sir? Just connect no two wires. What are all these things over here? See, I'll tell you what. If you, I think you know this also, but still, if you directly pass the voltage from the, power plant to your house, this distance is usually huge. It's not like you stay beside the power plant, or else you'll be breathing some harmful gases. So obviously, this will be not in 1 or 2 kilometers. This will be generally hundreds of kilometers. Okay, hundreds of kilometers. So what happens because of that? If current is passing through that wire, if current is passing through that wire, the power loss in that wire which is carrying the current will be I squared into resistance of that wire. So think about it. The Papa power plant is generating some thousands and thousands of watts of energy, and because you are stupid enough that you didn't realize the current is very large, because obviously it has to go to so many houses, so much current will be there. It will be in kilo amperes and all, kilos of amperes, yes. So imagine that kilo square will become like mega, and you will cause so much of loss that the power plant is generating watts and watts of energy. What you are getting here is milliwatt. You can only light your LED bulb. It will be like one full flop show only. So you want to minimize the loss. So you want to minimize the loss. Minimize what? The loss. So what will you do? You will obviously minimize the current. So the transmission, whatever is transmission, is reduced. Transmission current is reduced. You can say, sir, resistance can be also reduced. Bro, how are you going to reduce resistance? Like, you use the best material, copper. Length is fixed. You cannot change the length. Area, how small can you make? Because if you make it too small, then the wire will only melt, carrying so much of current. So there is another problem. So you cannot use like superconductor and all that. That is not possible. So only way this can happen is if you reduce the current. How do I reduce the current, sir? Simple. You use a device called as a transformer. So what it does is it increases the voltage like crazily, 1,000 times, 100 times like that. So the current falls. The voltage increases, current will fall. Once the current reduces, power between this point and this point will reduce, power loss. The power which is lost in that wire will reduce. But then, sir, if the voltage is increased so much, I can't use such thousands of voltage into my house. So you need to reconvert it back. You reduce the voltage, again get back the current. Now, this is a small distance. Here, there will be hardly any loss. So you cannot have a large distance. This device is called transformer. And again, you enter, the current enters your house, which is of decent value, and voltage is also reduced. So this transformer steps up the voltage and reduces the current, thereby reducing the loss. And this transformer steps down the voltage, increasing back the current, and you get decent current, decent voltage into your house with minimal loss between these 2 points. Not these 2 points. Is this clear logic? Okay. Sir, I just remember Sir was his prime but end up old after infinite YouTube and many sessions about JEE, but still students give up. I didn't understand, William Joshua, what you mean by that. 12 physics is easy, sir, because some tell it is tough. Okay, if I tell you it is easy, what will you do? If I tell you it is tough, what will you do? If I tell you it is tough, then will you give up? If I tell you it is easy, will you do it? Then I will tell you it is easy. Then please do it. Okay, don't listen to others, because who are those others? I'll tell you, those are those students who are not in that 99 percentile zone. Okay, so people who act, people who are working, they will not think about all these things. The top 1 percentile, 100 to 99 percentile, they are not thinking about all these things. These are those students who are thinking about between 0 to 80, 0 to 90 percentile. That is where this knowledge is coming. Yeah. All right. Now, what is the transformer? It increases the voltage or decreases the voltage accordingly. So, what is there inside a transformer? It is based on the principle of Faraday's law of induction, mutual induction. So, it's basically concept of mutual inductance. You have two coils. AC passes through one coil and then reverses the direction. First like this, then goes like this. So, there is magnetic field which is produced. That magnetic field goes into the other coil, and because the current here in the first coil is changing, therefore the magnetic field is also changing, and the field, when it passes through the second coil, then it creates electricity in the second coil, and you may use that on the other side. The first coil is called primary, the output coil is called secondary, and the magnetic flux is being linked from primary to the secondary. That's the simple mutual inductance. Same thing what you learned in EMI chapter. Nothing different. But then, what is all this nonsense, sir? What is this rectangle over here? I'll tell you. So this is the input side, primary. This is the output side, which is the secondary. Now, if current is passing in the primary, it will create magnetic fields. The magnetic fields will go everywhere. But not all the field lines will go into the secondary. Many lines will just go somewhere in the air, which is a waste for me. I don't want that. So what I do is I use a ferromagnetic material like iron, soft iron. So ferromagnetic materials attract the field lines. So all those lines which are going there will now be pulled here. So instead of going away, now they go within the iron core. So you have maximum flux which is going into the secondary coil, thereby generating enough electricity and causing less wastage. So if the flux gets lost, it is called as a flux loss, and it is going to reduce the efficiency of a transformer. Wastage of energy is there. So you want to minimize it. So use a ferromagnetic material. Is that clear, everyone? Why we use a ferromagnetic material? Because we want maximum flux to go into the other side. But the moment you use a ferromagnetic material, there are other things which happen. What are those other things? Well. Ferromagnetic materials show one property called as hysteresis. And what is this hysteresis loss? When you magnetize a ferromagnetic material, demagnetize it, again magnetize it, in this process, it's not a reversible pure process. There is a loss of energy. So, when current is flowing, magnetic field line is going like this first time. Second time, the current will reverse, magnetic field will go like this. Again, the magnetic field will go like this, clockwise, anti-clockwise. So what will happen? The magnetic field lines here are continuously reversing. So this part are getting continuously magnetized, demagnetized, reverse magnetized, demagnetized, again magnetized. So in this process, what are you getting? You are getting a hysteresis cycle of the ferromagnetic material that will cause further loss. Getting my point? So these are some places where losses occur in a transformer. Another loss which happens is when the flux passes, okay, through this. It's not that electricity is only induced in this coil, but also in the iron core over here and over here and over here and over here, you will see there are small current loops which are formed. There are small current loops which are formed. Those are called eddy current loops. Eddy loops. Random loops of current here, loops are formed. So because of that, more loss will happen. More loss will happen in that transformer. That is also bad. And finally, do not forget, these windings are going to be long. So they will also have some resistance. So there will be a loss due to the number of turns that you are going to have in that coil. So there are four kinds of losses which you generally encounter inside a transformer. There are four kinds of losses which you encounter. The loss due to the windings, then the flux loss where the magnetic field goes away, not in the secondary coil. Third, hysteresis loss because of the ferromagnetic nature, and eddy current loss because of current loops being formed throughout that conductor. These are the four losses that you encounter. Okay, winding loss I squared R, hysteresis loop loss. Now, how do you reduce each one of them? I will tell you. First thing what you do is winding loss. Why does it come? Because the wire has some length. You can't reduce the length. You can't reduce the turns by so much. So what you do, you use a good quality wire. It has less resistance like copper. Okay. So low resistance like copper wire if you use, the losses will reduce in the windings. Don't use aluminum. Don't be cheap. Okay. Hysteresis loss. What do you do to reduce hysteresis loss? The hysteresis area which is there, that has to be reduced. So choose a ferromagnetic material which has a smaller area within that loop. So such a material is basically soft iron. So soft iron is found to have small hysteresis. So thereby hysteresis losses also can be reduced. Why susceptibility so large and positive? Uh, we have discussed this in ferromagnetism, like susceptibility, what it is, and all of that. Uh, I think we are deviating from the topic. Lewis, if you are asking, is susceptibility large for ferromagnetic? The answer is yes. For diamagnetic, it is negative, and for paramagnetic, it is a small positive number. And susceptibility plus one is relative permeability and all that. And relative permeability is a number which tells me relative number, which tells me how permeable it is for the magnetic field lines. So ferromagnetic materials allow a lot of field, so it's more permeable. So relative permeability is very high. So that's why the susceptibility is very high, if that's what you're asking. Okay, so soft iron is used. Next, for eddy currents which are created, which causes loss due to the small loops, they can be reduced by using laminations on the core. Thereby, those eddy loops are not formed on the metallic surface. So you use a laminated soft iron core. So that lamination is important. Last thing, flux. Flux loss can be minimized by using a ferromagnetic material. So yes, ferromagnetic core like soft iron solves that purpose as well. So maximum flux will pass through the secondary. Now using all these four techniques, it has been found that the losses in the transformer reduce so much that almost the transformer becomes 98 to 99% efficient in spite of all these four losses. So the modern transformers are usually more than 90%, but the good transformers are 98 to 99% efficient. Meaning, if you give 100 joules of energy on the input side, almost 99 joules to 98 joules will come on the other side every second. So hardly 1 or 2 joules might be lost, which is okay, acceptable, that happens. We are going to live with it. So thereby you get the concept of efficiency of a transformer, where you write output power by input power is basically output power by input power into 100 is basically the percentage efficiency of a transformer. Output power will be the output voltage into output current. Input power will be input voltage into the input current. So if you divide both of them, E2 I2 by E1 I1 into 100, that will give me the percentage efficiency of the transformer. Just now I mentioned, Lewis, even in a real transformer, even if you do all these things, some loss will be there. No, you can't reduce it to zero. You can't say laminating it will make eddy current zero. Eddy current will reduce. It will not become zero. Flux loss will reduce but not become zero. Winding loss will be there even in copper. Hysteresis will not become zero. It will still be there but less. So you can't get 100%. Okay, Lewis. Perfect. Okay. Now going to the final point over here. Yeah. So we discussed what losses are there, how to minimize the losses, and the efficiency of a transformer is the output by input into 100 in percentage. You can get up to 98-99 percentage with good, materials, choice of materials and windings. Okay. Now, what is the formula relating this primary side and secondary side? The answer for that is, if you use Lenz's law, if you use Faraday's law, my bad, and you say, this is like an inductor. Yeah, you can see this is a coil. This is like an inductor. Remember, E is L di by dt and all of that. Similar formulas if you use, you are going to get EMF's ratio or voltage ratio, primary by secondary, is N1 by N2, meaning number of turns on the primary side by turns on the secondary side is primary voltage by secondary voltage. As simple as that. That's it. E1 by E2 is N1 by N2. Very simple. Nothing great about it. But also do remember that for for negligible loss, what will happen? E1 I1 will almost be equal to E2 I2. It will not be less, it will be almost the same. So therefore, E1 by E2 will be I2 by I1 only when it is almost 100% efficient. Almost 100% efficient. So this one we already know, it is also N1 by N2. So therefore, N1 by N2 number of turns ratio is E1 by E2, but it is I2 by I1. So this is the final formula, only and only if it is 100% efficient. Otherwise, it will not be valid. Which part will not be valid? This part. This is anyways valid. E1 by E2 is N1 by N2. That is always valid, irrespective of whether it is real, ideal, whatever transformer. But the only problem happens is if it is not 100% efficient. Then this relation is no longer valid. Okay, perfect. All right, still watching. Very good, Namishwar. Thank you so much for pointing it out. Makes me motivated, man. What to tell? Okay, so we've done this. So it's time to do some questions now on your screen. We'll do that question first and then we'll come here. Okay, Primary side of a transformer is 230 volts, 50 hertz supply. Turns ratio is 10 is to 1. Resistance is 46 ohms. What is the power consumed? Okay, let's see. So we have 230 volts on the primary side, okay, on the primary side. If you talk about the secondary side, it has 46 ohms resistance. Winding ratio is given. This is 10 is to 1. So from this, we can easily say whatever is the secondary voltage, primary by secondary voltage is the turns ratio. So therefore, V2 will be 23 volts. V2 will be 23 volts directly. Okay, what do I do with it? Once I know the voltage, we can also find what might be the power in it. So the power will be V square divided by R. Voltage is 23, so 20 square divided by 46. So this is 23 multiplied by 23. 46 is 23 multiplied by 2. 23 cancels, 23 by 2. Yep, guys, how much is it? It's going to be 11.5. Is that right? 11.5. So hence the answer will be option A. That's the answer. Very simple and sweet type of question. Let's do another question. The first question actually. Primary coil, secondary coil, 220 volts, 110 respectively. Secondary coil is connected to resistances as shown. The output voltage is how much? Now many people got confused in 2024. So what to do if such a circuit comes? Bro, you don't have to break your head so much. I'll tell you what. See, primary, secondary turns of the transformer are given. So that's it. V1 by V2 is simply N1 by N2. V1 is 220. Secondary voltage, we do not know. We have to figure it out. And N1 and N2 is 100 divided by 10. 0, 0 cancels. This 0 also cancels. So 22 by V2 is basically 1. So V2 is basically 22 volts. It is basically 22 volts. That's it. Just mark it, guys. But you will see that the answer is something else only. Okay. The answer is something else only. What has gone wrong? What has gone wrong? Think about it. That is not the correct answer. Lot of people will do this because they will get confused over here, like I said. And this is exactly what was asked in 2024. The problem is this V2 of 22 volts is not over here. The question is, what is the voltage here? That 22 volts is technically over here. 22 volts is over here. Think of this now like a new circuit where there is a battery of 22 volts and there is a resistance here and there is a resistance here. Now solve it. This is 15 kilo ohm. This is 7 kilo ohm. Now, what you should do is first figure out how much current will be there in the circuit, guys. And that current will be the voltage divided by the total resistance, which is 15 plus 7 kilo. So that will be 22 by 22 kilo. So that will be 1 milliamperes because this is kilo, right? So kilo means 10 to the power 3. So this will be amperes. That will be 1 milliampere. From that current, now figure out how much voltage will be there over here. That will be the current multiplied by that particular resistance. So the current is 1 milliampere. Resistance is 7 kilo ohm. So milli and kilo will go. So only 7 will remain. So 7 volts will be then the correct answer. Got it? So this was a very good question because many people they end up marking 22 volts, which is also there. But that was a trick which was there. That voltage is across the secondary coil, not this voltage, as per this diagram. Yeah, a lot of people make that mistake. Moving on. Now, yeah, this is also done. Oh yes, I had a question which I wanted to give you, which is based on not 100% efficiency. Imagine there is a transformer. It is given that the uh, the primary voltage is example 200 volts. The primary current is given to be, let's say, 4 amperes. Ratio of primary is to secondary. Ratio of primary is to secondary is given as 1 is to 10. It is given that the efficiency of such a transformer is just 80%. Find both V secondary and current in the secondary. Both of them you have to find. What are those values? Find the current and voltage in the secondary if it is 80% efficient. Now, whenever you get such a question, remember which formula is applicable and which one is not. It's only the voltage and turns ratio formula which is always applicable. So you can still write V primary by V secondary is N primary by N secondary, and this ratio is 1 by 10. V primary is 200. V secondary I do not know. So V secondary 10 into 200, which will make it 2000 volts. So V secondary we can directly find it out. The problem is only with I. I cannot write I1 by I2 is V2 by V1. That is no longer valid. So what I will do is, because it is mentioned 80% efficiency, so that 80% is basically output by input. Output is nothing but V2. So if you want, I can just write it down like this, that percentage efficiency is E secondary V into current upon V into current, but for primary into 100. This is what it actually means. Output by input into 100 is the percentage efficiency. So 80% will be voltage in secondary, we just got it as 2000. Current, I do not know. Voltage and current 204. Okay, and this is basically 100. So 0, 0 cancels, percentage also cancels. So I can just write 8 is equal to 0, 0, 2, 2 also cancels, 10 is there, IS is there, 4 is there. Okay, what else is gone? 0 and 0 is gone. So one more 10 is remaining. That's all. So therefore, my IS will be 8 multiplied by 4 divided by 10 into 10, which is 32 divided by 100, which is 0.32 amperes. That is the correct one. So 0.32 amperes is the current in the secondary. So this type of questions can also come where you have efficiency given. Sometimes they might give you the currents and ask you what is the efficiency. Both kind of questions are possible. Okay. So I kept a homework question for all of you after all of this marathon. Obviously, one question though you should be able to solve on your own. Okay. Transformer primary voltage and secondary voltage are given. The power is also given. Assume it is ideal, that means 100% efficiency. Then figure out what is the primary and secondary resistances on both the sides. Hint, power is V square by R. If you know this, your job is done. Power is V square by R. That's all. Okay. So that's your hint. Solve the question, mark the answer. Solution will be there in the PDF. You can download the PDF after the session is over. It will take some time. Obviously, it won't come now. It will come by tomorrow. So it will be there somewhere over here in the description box. Okay. So make sure you check it out and download it. Yeah, all my handwritten notes, the beautiful colored diagrams, everything. So after today's class, there is nothing that you cannot do after from AC circuits. Okay. So all the best. Hope you loved it. Smash the like button and stay subscribed. Thank you so much. Captain Shreyas signing off. I'll see you very soon. Take care. Bye bye.